In this video, you will explore whether information is fundamental to physics. Don't worry, this is not one of those brain-freezing physics lectures that are difficult to follow. Instead, the ideas are presented in an easy, relaxed and accessible way. Simply sit back, listen, and immerse yourself in the fascinating realm of physics. This video is designed to help you grasp advanced physics concepts with minimal effort. While it won't promise to offer you Harvard or MIT level depth, it will still provide meaningful insights and valuable understanding. Imagine for a moment that everything you have ever touched, everything you have ever seen, everything you are, is not actually made of matter at all. Imagine that the real substance of the universe, the thing that everything else emerges from, is something far stranger, something invisible, something that exists in patterns and relationships rather than in solid form. What if I told you that the atoms in your body, the light hitting your eyes right now, even the empty space between the stars, might all be different arrangements of the same fundamental thing? And what if that thing is not matter or energy, but pure information? This sounds like science fiction. It sounds like the kind of wild speculation you would expect from a philosopher in an ivory tower, not from serious physicists working with real mathematics and real experiments. But over the last 50 years, some of the brightest scientific minds on Earth have come to a startling conclusion. They have discovered evidence that information is not just something we use to describe reality. Information might actually be reality at its deepest level. By the end of our journey together, you will understand why the smartest physicists alive believe this. You will see the evidence they have found. And I promise you this: you will never look at the world around you the same way again. The screen you are watching right now, the thoughts moving through your mind, the sensation of time passing, all of these things are about to become far stranger and more wonderful than you ever imagined. But this is not just a story about abstract ideas. This is a story about a mystery that took decades to solve. A mystery that started with impossible quantum experiments, led to a 30-year war between brilliant scientists, and ended with a discovery so profound that it is still reshaping all of physics. This is the story of how we discovered that information is the hidden code underlying everything. Chapter 1. The Strange Beginning. Our story begins in the 1980s with a physicist named John Wheeler. Now, Wheeler was not some unknown researcher working in obscurity. This was a man who had worked on the Manhattan Project alongside the legends of 20th century physics. He had been a student of Niels Bohr, one of the founders of quantum mechanics. He had coined the term black hole back in 1967. When Wheeler spoke, physicists listened. So when Wheeler started saying something very strange in his later years, people paid attention even though they did not quite understand what he meant. Wheeler kept repeating a cryptic phrase. He would say, "it from bit." Just those 3 words, "it from bit." What on earth did that mean? Wheeler explained it this way. He said that every IT, every particle, every field of force, even space-time itself, derives its very existence from simple yes or no answers to questions, from bits of information. He was saying that the universe is not made of stuff that happens to contain information. Rather, the universe is made of information, and stuff emerges from that. This seemed crazy to most physicists at the time. They thought Wheeler might be losing his edge in his old age, getting too philosophical, drifting away from real physics into word games. But Wheeler was not just making up pretty phrases. He was trying to tell everyone something he had seen in the equations. Something that quantum mechanics had been hinting at for decades, but nobody wanted to face directly. You see, Wheeler had spent his whole career thinking about quantum mechanics, that strange theory that describes how atoms and particles behave. And quantum mechanics had always been weird. It had always produced results that seemed impossible, that seemed to violate our common sense about how reality works. But it was the weirdness itself that had caught Wheeler's attention. Because buried in that weirdness was a clue about information. Let me tell you about the experiment that started it all. It is called the double-slit experiment, and even though it was first done over 100 years ago, it still has the power to shock anyone who really thinks about what it means. Here is how it works. You take a light source and you shine it at a barrier, a screen that has two narrow slits cut into it. Behind that barrier, you put a detector screen that lights up wherever light hits it. Simple enough, right? When light goes through the two slits, it creates a pattern on the back screen. But here is the strange part. The pattern you see is not what you would expect if light were simply going through one slit or the other. Instead, you see an interference pattern, bright and dark bands that alternate across the screen. This makes sense if light is a wave. Waves do this. When you have two sources of waves, like dropping two pebbles in a pond, the waves spread out and overlap. Where two wave peaks meet, they add together and make a bigger wave. Where a peak meets a trough, they cancel out. This creates a pattern of high spots and low spots. So the double-slit pattern tells us that light is behaving like a wave that goes through both slits at once, then interferes with itself. But then someone decided to do the experiment with the light turned down so low that only one particle of light, one photon, goes through at a time. You might think that a single particle would have to go through one slit or the other, right? It cannot split in half. So you might expect to see two simple bright spots on the back screen, one behind each slit. But that is not what happens. Even when you send photons through one at a time, so that there is never more than one photon in the apparatus at once, the pattern that slowly builds up is still the interference pattern. Each single photon somehow produces a pattern that only makes sense if the photon went through both slits and interfered with itself. A single particle is behaving like a wave spread out over space. But wait, it gets stranger. Because then someone said, well, let us just watch which slit the photon goes through. Let us put a detector at the slits that tells us which path the photon takes. And here is where things become impossible to ignore. The moment you try to detect which slit the photon goes through, the interference pattern disappears. Now you just get two bright spots, as if the photon went through one slit or the other like a normal particle. Read that again. When nobody is watching, the photon behaves like a wave and creates interference. When someone watches, it behaves like a particle and goes through one slit. The photon seems to know whether it is being observed or not, and it changes its behavior accordingly. Now, when physicists say observed here, they do not mean observed by a conscious mind. They mean interacted with by a measuring device, something that records information about which path was taken. But that is exactly the point. It is the presence or absence of information about the photon's path that determines how the photon behaves. When there is no information available about which path was taken, the photon acts like a wave. When information exists about the path, the photon acts like a particle. This is what Wheeler saw. This is what made him say it from bit. The physical behavior of the photon, the IT, depends on whether or not information about it exists, the bit. Information is not just passively describing what happens. Information is actively involved in determining what happens. Wheeler pushed this idea further. He designed thought experiments where you could choose whether to measure the path information even after the photon had already gone through the slits. And the mathematics of quantum mechanics predicted that your choice would still affect what happened, as if the photon somehow knew your future choice and behaved accordingly. Wheeler called these delayed choice experiments, and they have since been performed in laboratories. The predictions were correct. The choice of what information to gather affects what happened in the past. This is not magic. This is not mysticism. This is what the equations of quantum mechanics have been telling us all along. But Wheeler was one of the first to really emphasize what this means. It means that information plays a fundamental role in physical reality, not just as something we calculate or measure, but as something that determines what actually happens. So when Wheeler said it from bit, he was not being poetic. He was trying to warn everyone that we had been thinking about physics backwards. We thought information was something that described physical things. But maybe physical things are actually patterns of information. Maybe the universe is, at its deepest level, made of answers to yes or no questions, made of bits. Most physicists in the 1980s heard this and nodded politely and went back to their normal work. They thought, "Interesting idea, John, very philosophical, but we have real physics to do." They were wrong to ignore him, because over the next 40 years, physics would be turned inside out. And the trigger for that revolution would be the strangest objects in the universe. Black holes. Chapter 2. What even is information? Before we can understand why information might be fundamental to physics, we need to understand what physicists mean when they say information. Because in physics, information means something very specific. It is not quite the same as what we mean when we talk about information in everyday life. When you think about information, you probably think about things like the news, or a text message, or the contents of a book. You think about meaningful content, knowledge about something. But in physics and mathematics, Information has a much more precise definition that does not necessarily have anything to do with meaning or knowledge at all. Let me show you what I mean with a simple example. Imagine I'm about to flip a coin. Right now, before the flip, you do not know whether it will land on heads or tails. There are two possible outcomes, and you have no way to predict which one will happen. The coin is in a state of uncertainty from your perspective. Now I flip the coin and I look at it, but I do not show you yet. I now know the outcome. I have gained information. Specifically, I have gained one bit of information. A bit is the basic unit of information, and it represents the amount of information needed to distinguish between two equally likely possibilities. Heads or tails, yes or no, on or off, 0 or 1. Each of these is one bit of information. Now I show you the coin. You see, it is heads. You have now also gained one bit of information. Your uncertainty about the coin has been reduced. Before, there were two possibilities. Now you know which one is real. That reduction in uncertainty, that is what information measures. Information is about narrowing down possibilities. If I told you I am thinking of a number from 1 to 8, and I asked you to guess it, how much information would you need to figure it out? Well, with yes or no questions, you could do it in 3 guesses. Is it bigger than 4? Is it bigger than 6? Is it odd? With 3 bits of information, 3 yes or no answers, you can distinguish between 8 possibilities. In fact, 3 bits can encode exactly 8 different values, because 2 times 2 times 2 equals 8. This is why computer memory is measured in bits. Every piece of data in a computer, every number, every letter, every pixel in an image is encoded as a string of zeros and ones, a sequence of bits. A kilobyte is about 8,000 bits. A megabyte is about 8 million bits. A gigabyte is about 8 billion bits. The book you read last week might contain a few million bits of information. The human genome, or the DNA information that describes how to build a human being, contains about 6 billion bits. So information in the technical sense is just about the number of yes or no questions you need to answer to specify something completely. It is about distinguishing possibilities. And here is the key insight that carries over from information theory to physics. Information can be measured. It is not fuzzy or subjective. Given a system with a certain number of possible states, there is a precise amount of information needed to specify which state it is in. But physical information has properties that go beyond just counting bits. The most important property was discovered by a physicist named Rolf Landauer in 1961. Landauer realized that information is physical. This sounds obvious, but it was actually a profound insight. What Landauer meant was this: information always has to be encoded in some physical system. It could be the orientation of magnetic domains on a hard drive, or the electrical charge in a computer chip, or the positions of molecules in your brain, or the patterns of ink on a page. You cannot have information floating around by itself with no physical representation. Information always lives in something. And because information is physical, it is subject to physical laws. In particular, Landauer showed that erasing information requires energy. When you delete a file from your computer, when you forget something, when you destroy information in any way, you have to pay an energy cost. The universe demands that cost. This is called Landauer's principle, and it connects information to thermodynamics, the physics of heat and energy. Think about what this means. It means information is not abstract. Information is as real as energy or matter. You cannot create or destroy it for free. There are physical consequences to manipulating information. This was the first hint that information might be more than just a human concept we invented to describe things. Information might be built into the fabric of reality itself. But there is something even deeper going on with physical information. In quantum mechanics, physicists discovered something shocking. Information cannot be created or destroyed. This is not quite the same as Landauer's principle. This is saying something more fundamental. The total amount of information in the universe is conserved. Let me explain what that means. In physics, when we say something is conserved, we mean that the total amount of it never changes. Energy is conserved. You can convert energy from one form to another, but you cannot make it or destroy it, you can only transform it. The same goes for momentum, angular momentum, electric charge. These are the great conservation laws of physics, and they turn out to be deeply connected to the symmetries of nature. And now we know that information is also conserved in quantum mechanics. When a quantum system evolves in time, the total information content stays the same. You might change what form the information takes. You might spread it out or concentrate it. You might make it harder or easier to access, but you cannot actually eliminate it. This is called unitarity in quantum mechanics, and it is one of the most fundamental principles of quantum theory. The equations of quantum mechanics are constructed in such a way that information is always preserved. Every quantum process can, in principle, be reversed. Nothing is truly forgotten. Now, you might object here. You might say, wait a minute, what about when I burn a book? The information in that book is destroyed, right? The ashes do not tell me what the book said. Or what about when ice melts into water? The orderly crystal structure is gone. That information is lost. And this is the cliffhanger I want to leave you with as we finish this chapter. Because this question about what happens to information when you burn a book or melt ice or scramble an egg, this question is going to lead us into the deepest mystery in all of physics. The mystery that started a 3-decade war between the smartest scientists alive. The mystery of what happens to information when it falls into a black hole. But before we get to black holes, we need to understand how we got here. We need to understand the 3 great revolutions in physics that set the stage for our story. Because this is not really a story about information. This is a story about how 3 different ideas that seemed separate for most of the 20th century, suddenly turned out to be talking about the same thing. Chapter 3. The 3 Revolutions. To understand why physicists started taking information seriously, you need to know about 3 separate revolutions that happened in physics during the 20th century. At the time, these revolutions seemed to be about completely different aspects of reality. But by the end of our story, we will see that they were all part of one big revolution. The revolution that would show us information is fundamental. The first revolution was relativity. In 1905, Albert Einstein published a paper that changed everything we thought we knew about space and time. He showed that there is no such thing as absolute time, no universal clock ticking away the same for everyone in the universe. Instead, time is relative. Time passes at different rates depending on how fast you are moving and how strong the gravity is where you are. This sounds impossible. How can time be flexible? But Einstein showed that it had to be true to explain some strange experimental results. Light always moves at the same speed, no matter how fast you are moving when you measure it. This seems to violate common sense. If you are on a train moving forward and you shine a flashlight in the direction the train is moving, shouldn't the light be going faster, the speed of the train plus the speed of light? No. The light still goes at exactly the same speed as if you were standing still. The only way to make this work is if time itself adjusts. If you are moving very fast, time slows down for you compared to someone standing still. Not by much at everyday speeds, but as you approach the speed of light, time dilation becomes extreme. This is not an illusion. It is real. Atomic clocks on fast airplanes tick slower than clocks on the ground. GPS satellites have to account for relativity or they would not work. Einstein went further. In 1915, he developed general relativity, which showed that gravity itself is really the curvature of space-time. Mass and energy bend space and time around them, and what we call gravity is just objects following the curves in space-time. This means space and time are not separate things. They are unified into a single entity, space-time. Now, what does this have to do with information? Here is the connection. In relativity, there is an absolute speed limit in the universe. Nothing, not matter, not energy, not even information, can travel faster than the speed of light. This speed limit is not arbitrary. It is a fundamental property of space-time itself. This means that information has a maximum speed. If something happens on Mars right now, the information about that event cannot reach Earth faster than light can travel, which takes several minutes. There is no way to communicate faster. This creates something called the light cone. Any event can only influence other events that lie within its future light cone, the region that light from that event can reach. This might seem like a constraint, like a limitation, but it is actually telling us something profound. It is telling us that information propagation is a fundamental aspect of how causality works in the universe. Events are connected by the flow of information between them. The structure of space-time itself is tied to how information can move through it. Relativity was the first hint that information is not separate from physics. It is woven into the geometry of space and time. The second revolution was quantum mechanics. In the 1920s and 30s, physicists discovered that at the smallest scales, reality does not behave the way we expect. Particles do not have definite positions and velocities until you measure them. Instead, they exist in superpositions, being in multiple states at once, and only collapse to a single outcome when observed. This was so strange that even the founders of quantum mechanics argued about what it meant. Einstein famously hated it. He said God does not play dice with the universe. He thought quantum mechanics must be incomplete, that there must be some deeper reality underneath where things are definite even when we are not looking. But experiment after experiment proved him wrong. Quantum mechanics is how reality actually works. At the heart of quantum mechanics is uncertainty. Not just our uncertainty about things, but fundamental uncertainty built into nature itself. There are pairs of properties like position and momentum, where the more precisely you know one certain the less precisely you can know the other. This is not because of limitations in our measuring instruments. This is a fundamental limit on what information can exist simultaneously about a quantum system. Think about what this means. There is a limit to how much information can be encoded in a physical system. You cannot have complete information about everything. The universe itself does not contain that much information. Quantum mechanics is imposing fundamental limits on information storage and processing. And here is something even stranger. When you measure a quantum system, you get information about it, but you also change it. The act of measuring, of extracting information, physically affects the system. This is not clumsiness on our part. This is fundamental. Information extraction has physical consequences in quantum mechanics. There is also a bizarre phenomenon called entanglement. Two quantum particles can become correlated in such a way that measuring one instantly affects the other, no matter how far apart they are. Einstein called this spooky action at a distance, and he thought it proved quantum mechanics was wrong. But it is real. Experiments have confirmed it over and over. What is entanglement really? It is shared information. The two particles together have a certain total amount of information, but individually neither particle has definite properties. The information is stored in the correlation between them, not in the particles themselves. This was another hint that information has a reality independent of the physical objects that carry it. So quantum mechanics was showing us that information is limited. Information extraction changes things, and information can exist in relationships between objects rather than in the objects themselves. This was revolution number 2. The third revolution was information theory itself. In 1948, a mathematician and engineer named Claude Shannon published a paper called A Mathematical Theory of Communication. Shannon was working for Bell Labs, trying to figure out the best ways to send messages through noisy telephone lines. What he ended up creating was a completely general theory of information. Shannon defined information precisely in terms of uncertainty reduction, just like we talked about earlier. He showed that you could measure information, compress it, transmit it through channels, and there were fundamental limits to how efficiently you could do these things. He proved theorems about the maximum rate at which information could be transmitted through a noisy channel without errors. But Shannon was not thinking about physics at all. He was thinking about engineering and communication. Information theory was initially seen as something separate from physics, a mathematical tool that engineers could use. Yet some physicists noticed something interesting. Shannon's definition of information looked exactly like the definition of entropy in thermodynamics. Entropy is a measure of disorder, of how spread out and random things are. The second law of thermodynamics says that entropy always increases over time. Things get more disordered, more mixed up, more random. This is why eggs scramble but never unscramble, why mixing cream into coffee is easy but separating them back out is impossible. And Shannon's information formula was mathematically identical to Boltzmann's formula for entropy from the late 1800s. This could not be a coincidence. But what did it mean? Were information and entropy actually the same thing? A physicist named Léon Brillouin was one of the first to explore this connection seriously. He showed that the entropy of a system is really just a measure of our missing information about that system. When you know everything about the microscopic state of a gas, every molecule's position and velocity, the gas has no entropy from your perspective. But when you only know macroscopic properties like temperature and pressure, you are missing a huge amount of information about the details. That missing information is the entropy. When ice melts, when a book burns, information is not destroyed, it is scrambled. It gets dispersed into the random motions of countless molecules, into heat, into the environment. It becomes practically impossible to recover, but in principle, according to quantum mechanics, it still exists somewhere. The universe remembers even if we cannot read the memory anymore. This connection between information, entropy, and thermodynamics would turn out to be crucial, because in the 1970s, a physicist named Stephen Hawking was about to discover that black holes have entropy. And when you have entropy, you have information. And that raised a question that would take 40 years to answer. If black holes have information, what happens to it when the black hole evaporates? So, by the middle of the 20th century, physics had been revolutionized 3 times. Relativity had shown that space-time has structure and that information cannot travel faster than light. Quantum mechanics had shown that information is limited, physical, and encoded in relationships. Information theory had shown that information could be measured and that it was deeply connected to entropy and disorder. These 3 ideas were sitting there, like puzzle pieces, waiting to be put together. But nobody knew yet that they fit together. Nobody realized they were all part of one picture. That realization was going to come from the strangest place imaginable. It was going to come from black holes. We have just seen 3 revolutions in 20th century physics: relativity, quantum mechanics, and information theory. Each one changed our understanding of reality, but they seemed like separate ideas, different aspects of nature that did not necessarily connect to each other. That was about to change. Because in the 1970s, physicists began studying black holes in detail. And what they discovered was so shocking, so impossible to reconcile with what they thought they knew, that it started a war. Not a war with weapons, but a war of ideas, a battle that would last 30 years and involve some of the greatest minds in theoretical physics. This war was about a single question: do black holes destroy information? On one side was Stephen Hawking, perhaps the most famous scientist on Earth, arguing, yes, information is destroyed, deal with it. On the other side was Leonard Susskind and others arguing, no, information cannot be destroyed, and we need to rethink reality to understand why. The stakes of this war could not have been higher. If Hawking was right, then quantum mechanics, the most successful theory in the history of science, was wrong at a fundamental level. If Susskind was right, then we needed to completely rethink what space and time actually are. Either way, physics was about to be turned upside down. This is the story of the Black Hole Wars. Chapter 4. Black holes enter the story. To understand the war, you first need to understand what a black hole actually is. And I promise you, the reality is even stranger than the science fiction version. Black holes came out of Einstein's equations. In 1915, Einstein published his theory of general relativity, which describes gravity as the curvature of space-time. Massive objects bend the space and time around them. The more massive and concentrated the object, the more extreme the curvature. Just months after Einstein published his theory, a German physicist named Karl Schwarzschild found an exact solution to Einstein's equations. He was looking for the space-time geometry around a point mass, a perfectly spherical mass concentrated at a single point. What he found was bizarre. Schwarzschild discovered that if you compressed enough mass into a small enough volume, the curvature of space-time would become so extreme that a boundary would form. Inside this boundary, space-time would be curved so intensely that not even light could escape. This boundary is called the event horizon. Imagine drawing a sphere around a compressed mass. If the mass is compact enough, this sphere becomes a one-way membrane. Anything, absolutely anything, can fall inward across this boundary. But nothing, not matter, not light, not even information, can come back out. Once you cross the event horizon, you are trapped inside forever, falling toward the center. This is what we call a black hole. It is called black because even light cannot escape, so it emits no light at all. It is called a hole because things fall in and disappear from the outside universe forever. Einstein himself thought black holes were too weird to exist in nature. He thought they were just a mathematical curiosity, an artifact of pushing the equations to an extreme case that would never actually happen. He wrote papers trying to prove that nature would not allow black holes to form. But Einstein was wrong. Other physicists showed that black holes were not just possible, but inevitable. If you take a massive star and let it burn through all its fuel, nothing can stop it from collapsing. The star's own gravity crushes it smaller and smaller. If it is massive enough, nothing in nature is strong enough to stop the collapse. The star implodes past the point of no return and becomes a black hole. In the 1960s, astronomers started finding evidence for black holes. They found X-ray sources in the sky that seemed to be caused by matter spiraling into something invisible and incredibly massive. They found stars orbiting around apparently empty points in space, moving so fast that they could only be orbiting something with the mass of millions of suns compressed into a tiny region. By the 1990s, the evidence was overwhelming. Black holes are real. So by the time our story starts in the early 1970s, physicists knew black holes existed, and they knew the basic properties. A black hole has a mass, which determines how big the event horizon is. It has a spin, rotating at some rate, and according to general relativity, that is IT. Nothing else. Once matter falls in, all the details about what it was made of, how it was arranged, everything about its structure, all of that information disappears behind the horizon. From the outside, you can only measure the mass and spin. Everything else is hidden. This led to a famous saying among physicists: "Black holes have no hair." What they meant was that black holes are perfectly smooth and featureless. All the complicated details, all the hair as it were, gets shaved off when you make a black hole. Only the bare essentials remain visible from outside. And this is where the problem starts to appear. Think about what this means for information. Suppose you take two books, two completely different books with totally different contents, and you throw them both into a black hole. From the outside, after they have fallen in, there is no way to tell them apart. The black hole has slightly more mass now, but otherwise it is exactly the same. The information about what the book said, how they were different from each other, all of that is gone. Or is it? Maybe, you might think, maybe the information is still there, just hidden inside the black hole. We cannot see past the event horizon, but perhaps if we went inside, we would find the information still exists. The problem with this idea is that once you go inside, you can never come back out to tell anyone what you found. And you cannot stay inside for long anyway, because the tidal forces would rip you apart as you fell toward the center. So it seemed like information was simply inaccessible once it fell into a black hole. Hidden forever. But hidden is not the same as destroyed. Physicists could live with information being hidden. What they were about to discover was far more troubling. In the early 1970s, a young physicist named Jacob Bekenstein started thinking about black holes and entropy. Remember, entropy is a measure of disorder, of missing information. And the second law of thermodynamics says entropy always increases. Things always get more disordered, more random, never the reverse. But black holes seem to violate this law. If you took a hot gas which has lots of entropy, lots of disorder, and you threw it into a black hole, the entropy seemed to disappear. The black hole from the outside looked the same, perfectly smooth, with no disorder at all. The total entropy of the universe appeared to go down. This violated the second law. Bekenstein proposed a radical solution. What if black holes themselves have entropy? What if the event horizon, the surface of the black hole, has a measure of disorder associated with it? He showed that if you assign an entropy to the black hole that is proportional to the area of its event horizon, then the second law would still work. When matter with entropy falls in, the black hole's horizon grows, its area increases, and so does its entropy. The total entropy still goes up. But this raised a deep question. If a black hole has entropy, then it has information. Specifically, it has a huge amount of missing information about its interior. The entropy formula tells you how many different microscopic configurations could be hiding behind that smooth exterior. And that number is enormous. A black hole the mass of our Sun would have about 10 to the 77th bits of information hidden behind its horizon. So black holes do not actually eliminate information about what fell in. They store it, but they store it in a way that is completely inaccessible from outside. The information is encrypted in the most perfect encryption possible. There is no way to decode it, no way to figure out what is behind the horizon without crossing over yourself, and that is a one-way trip. This was the state of understanding when Stephen Hawking entered the picture. And what Hawking was about to discover would turn this entire picture upside down. Because Hawking found out that black holes are not perfectly black after all. Black holes glow. They emit radiation. They slowly evaporate. And when they evaporate, what happens to all that information? That question was going to start a war. Chapter 5. Hawking's Bombshell. In 1974, Stephen Hawking was a young theoretical physicist at Cambridge University, already well known for his brilliant work on black holes and cosmology. He was also suffering from ALS, a degenerative disease that was slowly paralyzing his body, though his mind remained as sharp as ever. Hawking had been thinking about what happens when you apply quantum mechanics near the event horizon of a black hole. Remember that quantum mechanics describes how particles behave at very small scales. One of the weird features of quantum mechanics is that empty space is not really empty. Even in a perfect vacuum, with no matter or energy present, quantum fields are constantly fluctuating. Virtual particles are constantly popping in and out of existence in pairs, a particle and its antiparticle, appearing briefly and then annihilating each other in a tiny fraction of a second. These quantum fluctuations happen everywhere all the time. They are a fundamental feature of quantum fields. Normally, they have no observable effect because the particles exist for such a short time and cancel out so quickly. But Hawking realized that something special might happen at the event horizon of a black hole. Imagine a pair of virtual particles, a particle and antiparticle, popping into existence right at the event horizon. Normally, they would come together and annihilate. But at the horizon, there is a chance that one particle falls into the black hole while the other escapes to the outside. The particle that escapes can now become real. It has enough time to exist before it would have annihilated, so it becomes an actual particle that flies away from the black hole. When Hawking worked through the mathematics carefully, he discovered something astonishing. These escaping particles would appear to an outside observer as thermal radiation, like the glow from a hot object. The black hole would be emitting radiation with a specific temperature that depends on its mass. Smaller black holes are hotter, larger ones are cooler. But all black holes emit this radiation. They glow. This is now called Hawking radiation, and it was one of the most important discoveries in theoretical physics of the 20th century. Hawking had found a direct connection between general relativity, quantum mechanics, and thermodynamics. Black holes are not cold, dark objects. They have a temperature. They emit heat. They behave like thermodynamic systems. But there was a problem buried in this discovery, a problem so serious that it would shake the foundations of physics. The problem was this: the Hawking radiation appeared to be completely random. It carried no information about what had fallen into the black hole. Let me explain why this was so shocking. The radiation comes from quantum fluctuations at the horizon. These fluctuations depend on the quantum fields near the horizon and the curvature of space-time there. They do not depend on what fell into the black hole a long time ago. Whether you threw in a book, a computer, a star, or a blob of random matter, the radiation coming out would be exactly the same thermal glow. It would contain no information about the stuff that went in. This means that as the black hole radiates, as it slowly glows and loses mass, it is emitting information-free radiation. Pure random heat with no structure, no data encoded in it. Over a very long time, the black hole would radiate away all its mass and disappear completely. And when it is gone, all the information about everything that ever fell in would be gone too, destroyed, eliminated from the universe. This is called the black hole information paradox, and it is one of the deepest problems in all of theoretical physics. Because if Hawking was right, if information really is destroyed by black holes, then one of the core principles of quantum mechanics is wrong. Remember what we said earlier. Quantum mechanics is unitary. Information is conserved. Every process in quantum mechanics can be reversed in principle. Nothing is truly forgotten. This is not just a nice feature of the theory. This is absolutely fundamental to how quantum mechanics works. If unitarity is violated, if information can be destroyed, then the whole mathematical structure of quantum mechanics collapses. We would need a completely new theory. Hawking understood this. He knew what he was saying, and his conclusion was stark and uncompromising. Quantum mechanics, he said, is not valid in situations involving black holes. Something has to give. Either we give up general relativity or we give up quantum mechanics. And since his calculation was based on both theories and seemed rock solid, Hawking concluded that we must give up unitarity. Information can be destroyed. Quantum mechanics must be modified. When Hawking announced this in 1974 and published his arguments, the physics community was stunned. This was not some random person making wild claims. This was one of the most brilliant physicists alive, using rigorous mathematics and arriving at a conclusion that seemed impossible to avoid. If Hawking radiation exists, and it seemed like it must, then information appears to be destroyed. Many physicists assumed Hawking must be right. If his calculation was correct and nobody could find an error in it, then we must accept the conclusion no matter how uncomfortable it makes us. Perhaps unitarity was only approximately true. Perhaps information could be destroyed. just very rarely, only in extreme situations like black holes. But there was one physicist who absolutely refused to accept this. His name was Leonard Susskind, and Susskind was convinced that Hawking was wrong, that information cannot be destroyed, that there must be something we are missing about how black holes work. Susskind's position was simple. Quantum mechanics is far too successful, far too well tested, far too fundamental to give up. If the calculation says information is destroyed, then there is something wrong with the calculation, not with quantum mechanics. This was the beginning of what Susskind would later call the Black Hole Wars. On one side was Hawking and his followers arguing for information loss. On the other side was Susskind and a growing group of physicists arguing for information conservation. The war would last for 30 years. It would involve some of the nastiest intellectual battles in the history of physics. And the resolution would be so strange, so profound, that it would force physicists to completely rethink what space and time actually are. Chapter 6. The War Begins. The Black Hole. Wars were not fought with weapons or violence, of course. They were fought with mathematics, with thought experiments, with heated debates at conferences, and with papers written in terse academic language that nevertheless conveyed deep disagreement. But make no mistake, this was a war. Reputations were on the line. Entire research programs depended on who was right. And at stake was nothing less than our understanding of reality itself. Leonard Susskind was in many ways the perfect opponent for Stephen Hawking. While Hawking was urbane, British, a product of Cambridge, and someone who worked in the most abstract reaches of cosmology, Susskind was brash, American, from working-class New York, and someone who prided himself on physical intuition and concrete examples. Where Hawking wrote in elegant mathematical prose, Susskind thought in pictures and mechanisms. They were opposites in personality and style, and they disagreed completely about the information paradox. Susskind's position from the very beginning was that information cannot be destroyed, period, end of story. This was not negotiable. Quantum mechanics demanded unitarity. If you gave up unitarity, if you allowed information to be destroyed, then you opened a Pandora's box of problems. Causality would break down. Energy would not be conserved. The entire logical structure of quantum mechanics would fall apart. To Susskind, preserving unitarity was worth any price, including giving up cherished ideas about space and time, if necessary. But where was the information going? That was the puzzle. Hawking's calculation seemed airtight. The radiation coming out of a black hole appeared to be thermal, random, carrying no information. So either information was being destroyed, or it was going somewhere else, somehow escaping in a way that Hawking's calculation missed. In the early 1980s, Susskind and others started proposing ideas. Maybe, they suggested, the information is not in the radiation that escapes to infinity. Maybe it is stored in subtle correlations in the radiation that are too complex to see in Hawking's approximate calculation. Maybe if you looked more carefully at the quantum state of the radiation, you would find all the information about what fell in, just scrambled in an incredibly complicated way. This became known as the idea that information comes out in subtle correlations. The radiation looks random if you measure any part of it in isolation. But if you collected all of the radiation, every single photon emitted over the entire lifetime of the black hole, and you measured its complete quantum state, then you would find the information. It would be encoded in the correlations between different bits of radiation, in the quantum entanglement structure. It would be there, just hidden in a way that requires you to analyze the entire output. Hawking and his supporters were not convinced. They argued that this was just wishful thinking. Hawking's calculation was done carefully, and it showed that the radiation at any given moment was in a thermal state, uncorrelated with what had been emitted before. Correlations between different parts of the radiation could not encode much information if each part was independently thermal. The math did not support Suskind's hope. The debate raged through the 1980s. Neither side could prove their case definitively. Suskind could not show exactly how the information got out. Hawking could not prove that his calculation had accounted for everything. They were at a stalemate. Then, in the early 1990s, something remarkable happened. Several physicists started exploring ideas from string theory, a radical new approach to quantum gravity that treats particles as tiny vibrating strings rather than points. String theory was developing rapidly in the 1980s and 90s, and it provided new mathematical tools for thinking about black holes. String theorists discovered something extraordinary. In string theory, you could count the microscopic states of certain special types of black holes. Remember that entropy measures the number of possible microstates. If a black hole has entropy, it means there are many different ways to arrange its interior structure. But nobody had ever been able to count those states explicitly because we do not have a complete theory of quantum gravity. String theory changed that, at least for certain simple black holes. Physicists like Andrew Strominger and Qumran Vafa showed that you could build black holes in string theory, count the number of quantum states they could have, and calculate their entropy from first principles. And the answer exactly matched Bekenstein and Hawking's formula for black hole entropy based on the horizon area. This was a huge triumph for string theory. It showed that black hole entropy was not just an analogy, it was real. Black holes really do have microscopic quantum states, a huge number of them, and string theory could count them. But this made the information paradox even more acute. If black holes have microscopic states, then information about what fell in should be encoded in which microstate the black hole is in. When the black hole radiates, that information should come out somehow, encoded in the radiation. But Hawking's calculation still seemed to show that it did not. The tension between quantum mechanics and the black hole calculation was getting worse, not better. The arguments continued through the 90s. Suskind remained convinced that information must be preserved. Hawking remained convinced it was lost. They argued at conferences. They gave dueling talks. The physics community was split. Nobody had a completely satisfying answer. Then, in the late 90s, something happened that changed everything. A young physicist named Juan Maldacena discovered something so profound, so unexpected, that it would eventually force even Hawking to change his mind. Maldacena found a proof of a holographic relationship between two different theories. And that discovery would lead to the strangest idea in all of physics. The idea that our three-dimensional world might be a projection from a two-dimensional surface. The idea that reality is a hologram. But before we get to that breakthrough, we need to understand where this holographic idea came from. Because the seeds of the solution to the black hole wars were planted in the early 90s by two physicists who had a wild intuition about how information might be stored in black holes, an intuition that at first seemed impossible but would turn out to be absolutely correct. And their names were Gerard 't Hooft and Leonard Susskind. For 20 years, the black hole wars had raged. Stephen Hawking argued that black holes destroy information. Leonard Susskind argued that information must be preserved, somehow, somewhere, even if we do not yet understand how. Neither side could prove their case. Neither side could find the smoking gun that would settle the debate once and for all. But buried in the mathematics, hidden in the structure of space-time itself, was a clue so strange, so counterintuitive, so alien to how we normally think about reality, that when physicists first suggested it, many thought it must be wrong. It could not possibly be right. It was too weird. The clue was this: maybe information is not stored inside black holes at all. Maybe it is stored on the surface, on the event horizon. And if that is true for black holes, maybe it is true for all of space. Maybe all of the information in our three-dimensional universe is actually encoded on a two-dimensional boundary, like a hologram. Maybe the universe itself is a holographic projection. This is the holographic principle, and it is one of the most profound ideas in modern physics. It solved the black hole wars. It connected quantum mechanics to gravity. And it suggested that space itself is not fundamental. Space emerges from information. Dimensions emerge from information. Everything at the deepest level is information arranging itself into patterns. This is the story of how physicists discovered that reality might be a hologram. Chapter 7. The Holographic Principle. In 1993, a Dutch physicist named Gerard 't Hooft was thinking about the information paradox from a new angle. 't Hooft was not someone to ignore. He had won the Nobel Prize in 1999 for his work on the mathematical foundations of quantum field theory. He was one of the deepest thinkers in theoretical physics, someone who understood the mathematics of quantum mechanics and relativity at a profound level. 't Hooft had been worrying about what happens to information near black holes, and he had a strange intuition. He noticed something peculiar about entropy and black holes. Remember that Bekenstein had shown that black hole entropy is proportional to the area of the event horizon, not the volume. This was odd. Normally, when you think about how much stuff can be stored in a region of space, you think about volume. A bigger box holds more things, but black hole entropy depends on surface area instead. This suggested something deeper. 't Hooft started thinking, What if all of the information about what is inside a black hole is actually encoded on the surface, on the horizon itself? Not inside the volume, but on the boundary. The horizon would be like a storage device, with each bit of information occupying a tiny area on the surface. If you think about it, this would solve the information paradox. When matter falls into a black hole, the information about that matter does not disappear into the interior. Instead, it gets absorbed into the horizon, encoded into the surface. When Hawking radiation is emitted, it comes from the horizon, and it could, in principle, carry information that is stored there. The information never actually goes inside the black hole in a way that gets lost. It is always on the boundary, always accessible from the outside. But 't Hooft went much further. He said, if this is true for black holes, maybe it is true for any region of space. Maybe all of the information in a volume of space can be described by information on the surface that bounds that volume. Maybe three-dimensional reality is actually encoded in 2 dimensions. This sounds impossible. How can you fit all the information from a 3-dimensional space onto a 2-dimensional surface? Wouldn't you lose information going from 3 dimensions to 2? But 't Hooft pointed to the mathematical analogy with holograms. You have probably seen a hologram. It is a flat piece of film that, when illuminated with laser light, projects a full 3-dimensional image. All of the information needed to reconstruct the 3-dimensional scene is encoded in the interference patterns on the 2-dimensional film. You are not losing information by going from 3 dimensions to 2. You are just encoding it differently. What 't Hooft was suggesting is that the universe might work the same way. Our entire 3-dimensional world, with all its complexity, all its structure, might be a projection from information encoded on a distant 2-dimensional surface, like a hologram, but real. This was the beginning of the holographic principle. Around the same time, Leonard Susskind was having similar thoughts. Susskind had been fighting the information wars for years, and he was desperately looking for a way to show how information could be preserved in black holes. When he heard about 't Hooft's idea, it clicked for him. This was it. This was the answer. Susskind developed the holographic principle more fully. He argued that there is a fundamental limit to how much information can be stored in any region of space. The limit is not set by the volume of the region, but by the area of its boundary. Specifically, the maximum amount of information in any volume is at most 1 bit per Planck area on the boundary surface. The Planck area is incredibly tiny. It is the area of a square whose sides are the Planck length, which is about 10 to the minus 35 meters. This is so small that it makes an atom look huge. But the point is, there is a maximum information density, and it depends on area, not volume. Why is this so shocking? Because in our everyday experience, information storage seems to depend on volume. A bigger hard drive stores more data. A bigger library holds more books. If you want to store more stuff, you make a bigger box. But the holographic principle says that at the most fundamental level, The storage capacity depends on the surface area of the box, not its volume. This means that as you make a box bigger, the ratio of information capacity to volume goes down. A box twice as wide has 4 times the surface area, but 8 times the volume. So the information density per unit volume decreases. The universe has less information density than you would naively think. But here is the real kicker. The holographic principle is not just saying that information could be stored on surfaces. It is saying that information is stored on surfaces, and that the 3-dimensional world we perceive is a kind of holographic reconstruction from that 2-dimensional information. This is where things get really strange. If our 3-dimensional space is holographic, then in some deep sense, space itself is not fundamental. The real fundamental description would be in terms of a 2-dimensional theory, and our 3-dimensional experience emerges from that lower dimensional description. We are, in effect, living inside a hologram. Susskind and T. Hooft published these ideas in the mid-90s, and the reaction was mixed. Some physicists thought it was brilliant. Others thought it was too speculative, too weird, too much like science fiction. How could 3 dimensions emerge from 2? What would the 2-dimensional theory even look like? And most importantly, was there any evidence for this, or was it just a clever idea that happened to solve the information paradox? The skeptics had a point. The holographic principle was speculative. It was based on thought experiments about black holes, but nobody had shown that it was necessarily true or how it would work in practice. It was an intuition, a suggestion, but not yet a proof. That was about to change. In 1997, a young postdoctoral researcher named Juan Maldacena made a discovery that shocked the entire physics community. He found an explicit example of holography, a precise mathematical correspondence between a theory of gravity in a certain type of space and a quantum theory on the boundary of that space. He found a proof that holography was real, and with that discovery, the black hole wars were essentially over. Susskind was right. Information is preserved. And the reason it is preserved is because space itself is holographic. Information is not stored throughout the volume. It is encoded on a boundary. And that changes everything about how we understand reality. Chapter 8. The ADS or CFT Revolution. Juan Maldacena was a soft-spoken young physicist from Argentina who had been working on string theory. In 1997, while he was at Harvard, he discovered something that would become one of the most important results in theoretical physics of the last 50 years. It is called the ADS-CFT correspondence, and it is a precise mathematical realization of the holographic principle. Let me explain what Maldacena found in the simplest terms I can manage. This is going to require some care because it is genuinely subtle, but the payoff is worth it. This is the heart of why physicists now believe information is fundamental. Maldacena was studying a special kind of space-time called anti-de Sitter space, or ADS for short. Anti-de Sitter space is a solution to Einstein's equations of general relativity. It describes a universe with a negative cosmological constant, which means it has a particular curved geometry. It is not like our universe, which appears to be flat or slightly positively curved. ADS space curves in a different way, like the inside of a saddle. One important feature of ADS space is that it has a boundary at infinity. If you travel far enough in any direction, you eventually reach the edge of the space. This boundary is not like hitting a wall. It is more like an asymptotic limit. But mathematically, you can define what happens at this boundary, and you can put a quantum field theory there. Now, here is what Maldacena discovered. He found that you could describe gravity in the interior of ADS space. The full three-dimensional plus time equals four-dimensional bulk, using a completely different theory that lives on the three-dimensional boundary, which has no gravity at all. The boundary theory is a conformal field theory, or CFT, a special type of quantum field theory. The precise statement is this: Type 2 B-string theory on five-dimensional ad space crossed with a five-dimensional sphere is exactly equivalent to n equals 4 super-Yang-Mills theory, a specific quantum field theory living on the four-dimensional boundary of that ad space. If you did not understand those technical terms, that is okay. The point is simpler than it sounds. What Maldacena showed is that these two theories, which seem completely different, are actually the same theory described in two different ways. They are dual to each other. Anything you can calculate in one theory, you can also calculate in the other theory, and you get the same answer. This is called a duality, and it is one of the most powerful tools in theoretical physics. When you have a duality, you can translate questions from one theory to the other. If a calculation is hard in one theory, maybe it is easy in the dual theory. You can use whichever description is more convenient for whatever you are trying to understand. But ADS CFT is not just any duality. It is a duality between a gravity theory in the bulk and a quantum theory on the boundary. This is extraordinary. It means that gravity, the curvature of space-time, the formation of black holes, all of the phenomena described by general relativity in the interior, can be completely described by a quantum field theory with no gravity at all, living on a lower dimensional boundary. This is holography made precise. The interior bulk space is higher dimensional, but all of the information about what happens there is encoded in the lower dimensional boundary theory. The bulk is a holographic projection from the boundary. Or equally well, you could say the boundary is a holographic description of the bulk. They are two ways of looking at the same thing. When Maldacena announced this in 1997, the response was immediate and overwhelming. Within months, hundreds of papers were being written exploring the implications. Physicists quickly confirmed that Maldacena's correspondence worked. They calculated properties of black holes in ad space using the boundary quantum field theory, and everything matched perfectly. Here is why this matters for the information paradox. In the boundary theory, there is no gravity, and there are no black holes. It is just a quantum field theory, and quantum field theories are unitary. Information is automatically conserved in the boundary theory. There is no way for information to be destroyed because the boundary theory obeys all the rules of quantum mechanics perfectly. But the boundary theory is completely equivalent to the bulk theory with gravity and black holes. So, if information is conserved in the boundary theory, it must be conserved in the bulk theory too. There is no escape. When a black hole forms in the bulk and then evaporates, emitting Hawking radiation, the entire process must preserve information because the equivalent process in the boundary theory preserves information. This was the smoking gun. This was the proof that Susskind had been looking for. Information cannot be destroyed by black holes because black holes, when properly understood in a holographic framework, are just another configuration of a quantum system that always preserves information. Hawking's calculation must have missed something. The information must come out in the radiation, encoded in subtle correlations that are too complicated to see in an approximate calculation, but which are definitely there. Maldacena's discovery did more than just solve the information paradox, though. It showed that holography is real. It is not just a vague principle or an intuition. It is a precise mathematical fact. Space can emerge from a lower dimensional description. Gravity can emerge from quantum mechanics. The interior geometry of space-time can be reconstructed from information encoded on a boundary. And here is perhaps the most shocking implication. In the ADS-CFT correspondence, the bulk space-time with all its geometry, all its dimensions, all its structure, is not fundamental. What is fundamental is the boundary theory. The boundary theory is more basic, more real in some sense. The bulk space emerges from the boundary. Space itself is a derived concept, not a fundamental one. Think about what this means. We normally think that quantum mechanics happens in space. Particles move through space, fields spread out over space, interactions happen at locations in space. We think space is the stage on which the quantum mechanical play unfolds. But ADS-CFT is telling us that we have it backwards. Quantum mechanics is fundamental, and space emerges from quantum mechanics. The stage is not fundamental, the stage is built by the actors. This was a complete reversal of how physicists had been thinking for centuries. Since Newton, we assumed space was fundamental, an absolute background in which everything else happened. Einstein modified that by making space-time dynamic, able to curve and bend. But even in Einstein's theory, space-time was still the fundamental arena. ADS-CFT says no. Space-time is emergent. What is fundamental is the quantum information encoded in the boundary theory. The physics community was stunned. ADS-CFT became one of the most studied topics in theoretical physics. Thousands of papers were written exploring its implications. Physicists found that you could use it to understand quantum entanglement, to study the thermalization of quantum systems, to model the behavior of strongly interacting particles like quarks and gluons. It became a tool for understanding quantum gravity, black hole physics, condensed matter physics, even aspects of nuclear physics. It unified areas of physics that had seemed completely separate. But there was still a problem lurking in the background. A problem that would continue to trouble physicists for years to come. It is called the firewall paradox. and it shows that even with holography, we still do not fully understand how black holes preserve information. We know they must preserve it, but the mechanism is still mysterious. And that mystery points to something deeper that we are still missing about the relationship between quantum mechanics and gravity. But before we get to that, there is one more chapter in the black hole wars that we need to close. Because despite all this evidence, despite ADS-CFT, despite the holographic principle, Stephen Hawking had not yet conceded. He was still arguing that information is destroyed, and the physics community was waiting to see if he would ever admit he was wrong. Chapter 9. Hawking concedes. For 7 years after Maldaceno's discovery, the black hole wars continued. ADS-CFT had convinced most physicists that information must be preserved, that Susskind was right, and Hawking was wrong. But Hawking himself remained unconvinced. He argued that ADS-CFT was beautiful mathematics, but that it did not apply to the black holes in our actual universe. Our universe is not anti-de Sitter space. It is flat or slightly de Sitter, not negatively curved like ADS. So maybe the holographic principle works in ADS space, but not in real black holes. Susskind and others argued back. They said the basic principle should hold regardless of the exact geometry. If holography works in one context, it should work everywhere. Information conservation is too fundamental to be geometry dependent. But Hawking was stubborn. He had built his reputation partly on the information paradox. Admitting he was wrong would not be easy. Then, in July of 2004, a major conference was held in Dublin, Ireland. The conference was about quantum aspects of space and time, and both Hawking and Susskind were scheduled to speak. Everyone in the physics world knew that this might be the moment when the information wars finally came to a head. Hawking spoke first, and to the astonishment of everyone in the room, he announced that he had changed his mind. He now believed that black holes do preserve information after all. Information is not destroyed. He had been wrong. The room erupted. This was one of the most famous scientists on Earth admitting a mistake on one of his most famous results. It made news around the world. There were headlines about Hawking conceding defeat in the black hole wars. Photographs of Hawking and Susskind together. It was a moment of triumph for Susskind and for everyone who had argued for information conservation. But Hawking's concession was more nuanced than the headlines suggested. He said that he now believed information escapes from black holes, but he proposed a different mechanism than what most physicists believed. He suggested that quantum fluctuations in the geometry of space-time might allow information to leak out during the formation and evaporation of the black hole, not just in the final moments. He was proposing a modification to how we calculate black hole evaporation. Not everyone was satisfied with Hawking's proposed solution. In fact, most physicists thought his specific mechanism was wrong or incomplete. But that was not really the point. The point was that Hawking had admitted the fundamental principle. Information must be conserved. Unitarity wins. Quantum mechanics is safe. The black hole information paradox is not a paradox after all. It is a puzzle about how information is preserved, not whether it is preserved. Susskind was gracious in victory. He later wrote that Hawking was wrong in the most interesting possible way. Hawking's original calculation and paradox had forced physicists to think deeply about the relationship between quantum mechanics and gravity. It had led to the holographic principle, to ADS CFT, to a complete reimagining of what space and time are. Without Hawking's provocative claim that information is destroyed, physicists might never have been pushed to discover these profound truths. So, in a sense, Hawking's error was incredibly productive. It was the right kind of wrong. It posed a challenge that forced the field forward. And that is often how science progresses. Not through people being right all the time, but through people being wrong in interesting ways that inspire others to find the truth. The Dublin Conference marked the end of the black hole wars, at least in their most contentious phase. The community had reached a consensus. Information is fundamental. It is conserved. Black holes preserve it through holographic encoding, and space itself emerges from quantum information. But even as this chapter closed, new questions were opening up. If information is fundamental and space emerges from it, then what exactly is information in this context? How does quantum information differ from classical information? And most profoundly, if space emerges from information, how exactly does that work? What is the mechanism by which information relationships create the experience of distance and dimension? These questions would drive the next phase of research, the phase we are living through right now, the phase where physicists are trying to understand not just that information is fundamental, but how information creates reality. And that story begins with a deeper understanding of entropy, that measure of disorder that turns out to be deeply connected to information itself. The black hole wars are over. Stephen Hawking has conceded. The physics community agrees that information is conserved, that black holes preserve it, that holography is real. Susskind and 't Hooft were right. Space emerges from information encoded on lower dimensional surfaces. But now that we know information is fundamental, we need to understand what that really means. How does information connect to everything else in physics? We have seen hints already. Entropy is connected to information. Quantum mechanics preserves information. Black holes store information on their horizons. But now we need to see the full picture. It turns out that information is not just fundamental to black holes and quantum gravity. Information is woven into every aspect of physics. It connects thermodynamics to quantum mechanics. It explains why time flows in one direction. It determines the maximum efficiency of engines and computers. It sets limits on what can be known about the universe. Information is everywhere, underlying everything. This is the story of how physicists discovered that all of physics is really the physics of information. Chapter 10. Entropy and information unite. Let us go back to the 19th century for a moment. Back before quantum mechanics, before relativity, even before Einstein was born. Back to the age of steam engines and the Industrial Revolution. Because it was in trying to understand steam engines that physicists first stumbled onto the concept of entropy. In the 1800s, engineers and scientists were obsessed with making better engines. They wanted to know the fundamental limits on how efficiently an engine could convert heat into work. A man named Sadi Carnot studied this problem and discovered something surprising. There is a maximum possible efficiency for any heat engine, and it depends only on the temperatures of the hot and cold reservoirs the engine operates between. No matter how cleverly you design your engine, you cannot exceed this limit. This led to the development of thermodynamics, the science of heat and energy flow. And at the heart of thermodynamics was a mysterious quantity called entropy. Entropy measures something about disorder, about the spreading out of energy, about irreversibility. And there was a law, the second law of thermodynamics, which said that entropy always increases. In any closed system, entropy never decreases. Things always get more disordered, never more ordered. But what is entropy really? For decades, physicists used it without fully understanding what it meant. Then, in the 1870s, an Austrian physicist named Ludwig Boltzmann had a breakthrough. He connected entropy to probability. Boltzmann said, "Think about a gas in a box. The gas is made of countless molecules, each bouncing around, colliding with each other and the walls. At the microscopic level, there is a specific state of the gas, defined by the position and velocity of every single molecule. But you do not know that microscopic state. You only know macroscopic properties like the temperature, pressure, and volume." Now, here is the key insight. There are many different microscopic states that all correspond to the same macroscopic state. If you rearrange the molecules a bit, swap their positions around, you still have a gas at the same temperature and pressure. Each different microscopic arrangement is called a microstate. The macroscopic state you observe is called a macrostate. And each macrostate corresponds to a huge number of possible microstates. Boltzmann defined entropy as a measure of how many microstates correspond to a given macrostate. The formula is beautifully simple. Entropy equals K times the natural logarithm of the number of microstates, where K is Boltzmann's constant. This formula is so important that it is carved on Boltzmann's tombstone in Vienna. What this means is that entropy is really a measure of your ignorance about the microscopic details. If a macrostate has high entropy, it means there are many possible microscopic states it could be in, and you do not know which one. You are missing a huge amount of information. If a macrostate has low entropy, there are fewer possibilities, less uncertainty, less missing information. Now, jump forward to 1948. Claude Shannon is developing information theory, trying to understand communication systems. And he derives a formula for the information entropy of a probability distribution. He calls it the uncertainty in a message source. And his formula looks exactly like Boltzmann's entropy formula. The same mathematical structure, the same logarithm, the same way of measuring uncertainty. This could not be a coincidence. Boltzmann's entropy and Shannon's information are the same thing. Entropy is missing information. When you do not know the microscopic state of a system, when you only know probabilities, The entropy measures how much information you are missing. It measures your uncertainty. Let me give you a concrete example. Suppose you have a coin that you know is heads up. You have complete information about its state. There is no uncertainty. The entropy is 0. Now, suppose you flip the coin but do not look at it. Now, there are two equally likely possibilities. Your uncertainty has increased. You are missing one bit of information about whether it is heads or tails. The entropy is now 1 bit. Or think about ice melting. When water is frozen in a crystal, the molecules are arranged in an orderly structure. There are relatively few ways to arrange them while maintaining that crystal structure. The entropy is low. When the ice melts, the molecules can be anywhere in the liquid water, in countless different arrangements. The entropy is much higher. What changed? You have lost information about where the molecules are. They could be in any of an enormous number of configurations, and you do not know which one. This connection between entropy and information is one of the most profound insights in all of science. It unifies thermodynamics, which is about macroscopic systems and energy flow, with information theory, which is about messages and data. It shows they are two views of the same underlying reality. And here is where it gets even deeper. Remember Bekenstein and Hawking's discovery that black holes have entropy proportional to their horizon area? That entropy also measures information. Specifically, it measures the information hidden behind the horizon, the information about what fell into the black hole, and how its interior is arranged. A black hole with a large horizon area has high entropy, meaning it could be in any of a vast number of internal quantum states, and from outside you have no idea which one. You're missing a huge amount of information. So now we have three things that turn out to be the same. Thermodynamic entropy from the 1800s, Shannon information entropy from 1948, and black hole entropy from the 1970s. They all measure uncertainty, missing information, the number of possible microscopic states. They are all aspects of the same concept. This unification tells us something extraordinary. It tells us that the second law of thermodynamics, that entropy always increases, is really a statement about information. What the second law is saying is that information tends to spread out, to disperse, to become harder to access. When you break an egg, the information about how the egg was structured gets scrambled into the random thermal motion of molecules. The information still exists, it is not destroyed, but it is so dispersed and mixed up that it becomes effectively impossible to retrieve. This gives us a new way to think about the arrow of time, why time flows in one direction. We remember the past, but not the future. We see eggs break, but never spontaneously reassemble. We see coffee and cream mix, but never separate. Why? Because entropy increases. Information spreads out. The future is the direction in which information becomes more dispersed and less accessible. But here is the deep question. If information is fundamental, if the universe is really made of information as Wheeler suggested, then the second law is not just describing what happens to information. It is describing the fundamental dynamics of reality itself. The flow of time might be nothing other than the flow of information from accessible to inaccessible states, from ordered to disordered, from concentrated to dispersed. This connects everything we have been talking about. Quantum mechanics says information is conserved. Thermodynamics says information spreads out and becomes inaccessible. Black holes seem to destroy information, but actually store it holographically on their horizons. And underlying all of this is the fundamental principle that information is what the universe is made of. But we still need to understand what makes quantum information special, because information in quantum mechanics has properties that classical information does not have. Properties that are essential for understanding how space and time emerge. Properties that we are about to explore. We have been talking about information for a while now. Information measured in bits, in yes or no answers. Information that can be copied, transmitted, processed. The kind of information that computers manipulate and that Shannon's theory describes. This is classical information. But the universe is not classical. At its deepest level, the universe is quantum. And quantum mechanics changes the rules about information in ways that are absolutely fundamental to how reality works. Quantum information is not just classical information with some noise or uncertainty added. It is something qualitatively different, with properties that seem impossible until you see the mathematics and the experiments proving they are real. Understanding quantum information is essential for understanding why physicists believe information is fundamental to physics. Because the strange features of quantum mechanics, the features that Einstein found so disturbing, are really features of how information behaves in quantum systems. And those features turn out to be the key to understanding how space itself emerges. This is the story of what makes quantum information quantum. Chapter 11. When information gets quantum. In classical information theory, the basic unit is the BT. A bit has two possible values, 0 or 1, heads or tails, yes or no. A classical computer processes bits, flipping them, combining them, storing them. When you write information down, when you transmit a message, when you store data, you are manipulating classical bits. In quantum information theory, the basic unit is the qubit, the quantum bit. And a qubit is something much stranger than a classical bit. A classical bit is always definitely either 0 or 1 at any given moment. But a qubit can be in a superposition of 0 and 1 simultaneously. It is both at the same time until you measure it. Let me be very careful here, because this is often misunderstood. When we say a qubit is in a superposition of 0 and 1, we do not mean we just do not know which it is. We do not mean it is secretly one or the other, and we just have not checked yet. We mean it genuinely exists in both states at once, in a way that has measurable physical consequences. How do we know this? Because of interference. Remember the double-slit experiment from the beginning of our story? A particle goes through both slits at once and interferes with itself. That interference pattern proves that the particle was really in a superposition of going through both slits, not that it went through one slit and we just did not know which. The interference would not happen if it were just classical ignorance. The same thing applies to qubits. A qubit in superposition can interfere with itself. You can make it do things that would be impossible if it were classically in one state or the other. This is not a matter of information we are missing. This is a fundamental feature of how quantum systems exist. Now, you might ask, if a qubit is in a superposition, why do we only ever see it as definitely 0 or definitely 1 when we measure it? Why don't we see the superposition directly? This is the famous measurement problem in quantum mechanics, and we will come back to it later. For now, the key point is that before measurement, quantum systems really do exist in superpositions, and this is provably different from just not knowing the answer. So that is the first weird property of quantum information: superposition. Qubits can exist in multiple states at once in a way that is fundamentally different from classical uncertainty. The second weird property is entanglement. This is where quantum information gets really strange. Two or more qubits can become correlated in a way that has no classical analogue. When qubits are entangled, the state of one qubit is intrinsically linked to the state of the other, no matter how far apart they are. Let me give you an example. Suppose you have two qubits. You can prepare them in a special entangled state where if you measure the first qubit and find it is 0, you will definitely find the second qubit is also 0. And if you find the first is 1, the second will definitely be 1. They are perfectly correlated. You might think, okay, so they are both in the same state, both 0 or both 1, and when you measure, you find out which. But that is not what is happening. Before you measure, neither qubit has a definite state. They are in a superposition. The first qubit is both 0 and 1. The second qubit is both 0 and 1. But they are correlated in such a way that when you measure one, the other instantly takes on the corresponding value, even if they are light years apart. Einstein hated this. He called it spooky action at a distance. He thought it was proof that quantum mechanics was incomplete, that there must be hidden variables that determine the outcomes in advance. But experiments have proven Einstein wrong. Entanglement is real. When you measure one entangled qubit, the other really does instantly take on a correlated value, no matter the distance. Now, this does not violate relativity. You cannot use entanglement to send messages faster than light. The measurement outcomes are random from your perspective, so you cannot encode information in them. But the correlations between the measurements violate what you could get with any classical system. This has been proven experimentally over and over. Entanglement is real, and it is uniquely quantum. What entanglement means is that quantum information can be stored in relationships between systems, not just in the systems themselves. The information about the correlated state is not in qubit 1 alone or in qubit 2 alone. It is in the correlation between them. This is fundamentally non-local. The information exists in the connection, in the entanglement structure. And here is why this matters for our story. When physicists started thinking about how space could emerge from information, entanglement turned out to be the key. because entanglement creates connections between parts of a quantum system. And those connections, those information links, can be thought of as creating a kind of space. Where there is entanglement, there is connection. Where there is no entanglement, systems are independent, disconnected. Space might emerge from the pattern of who is entangled with whom. But we are getting ahead of ourselves. First, there is a third weird property of quantum information we need to understand: the no-cloning theorem. In classical information, you can always make a copy. If you have a bit that is 0, you can create another bit that is also 0. You can copy files on your computer. You can photocopy a document. Copying classical information is easy, and we do it all the time. But in quantum mechanics, you cannot copy an unknown quantum state. This is called the no-cloning theorem, and it is a rigorous mathematical result proven in the 1980s. If you have a qubit in an unknown state, there is no physical process that can create a perfect copy of that qubit while leaving the original unchanged. Why not? It comes down to the fundamental structure of quantum mechanics. Copying would require you to measure the state, but measurement disturbs it. If the qubit is in a superposition, measuring it collapses the superposition, and you only learn one outcome. You cannot extract enough information to reconstruct the original state without destroying it. This has profound implications. It means quantum information is more fragile than classical information. It is harder to protect, harder to transmit, harder to process. But it is also more secure. If someone intercepts a quantum message, they cannot copy it without disturbing it, so you would know someone was listening. This is the basis of quantum cryptography, a method for completely secure communication. But more fundamentally, the no-cloning theorem tells us that quantum information is truly physical, in a way that classical information is not. You cannot separate the information from its physical embodiment. You cannot extract it and copy it freely. The information is the quantum state, and the quantum state is unique and irreproducible. So, quantum information has three crucial properties that classical information lacks: superposition, entanglement, and no cloning. These are not just technical details. These are fundamental features that make quantum information qualitatively different from classical information. And these features are essential for understanding the holographic principle, the emergence of space, and why information is fundamental to physics. In particular, entanglement is about to become incredibly important. Because in the last 15 years, physicists have discovered that quantum entanglement is not just a weird feature of quantum mechanics. It is the glue that holds space together. It is the mechanism by which space-time emerges from information. And that discovery is one of the most profound developments in modern physics. Everything we have talked about so far has been building to this moment. We have seen that information is conserved in quantum mechanics. We have seen that black holes store information holographically on their horizons. We have seen that space can emerge from a lower dimensional boundary in ADS CFT. We have seen that quantum information has unique properties like superposition and entanglement. Now we are ready for the biggest claim of all. The claim that would have seemed like insane speculation just a few decades ago, but that is now taken seriously by many leading physicists. The claim that space itself is not fundamental, that the three dimensions we move through, the geometry we inhabit, the distances between objects, all of this emerges from something deeper, and that something deeper is quantum information, specifically the pattern of quantum entanglement. This is where John Wheeler's vision of IT from bit becomes reality, not just as a vague philosophical idea, but as a concrete mathematical program showing how geometry emerges from information. This is where we see that information is not just important for physics. Information is physics at the deepest level. This is the story of how space emerges from quantum entanglement. Chapter 12. It from qubit. In the early 2000s, after ADS-CFT had been established and the holographic principle was widely accepted, physicists started asking a deeper question. Okay, we know that space-time in the bulk emerges from a quantum theory on the boundary. But how does it emerge? What is the actual mechanism? What aspect of the boundary theory creates the geometry of the bulk? The answer, it turns out, is entanglement. The pattern of quantum entanglement in the boundary theory determines the geometry of space-time in the bulk. More entanglement means more connection, which translates to proximity in space. Less entanglement means less connection, which translates to distance. Space emerges from the structure of quantum information. Let me try to explain this carefully because it is genuinely mind-bending. In the boundary theory of ADS-CFT, you have a quantum system spread out over the boundary. Different parts of this boundary theory can be entangled with each other. Some regions might be highly entangled, sharing lots of quantum information. Other regions might be weakly entangled or not entangled at all. Now, when you use the ADS-CFT dictionary to translate from the boundary theory to the bulk spacetime, the entanglement structure maps onto the geometry. Regions of the boundary that are highly entangled correspond to regions of the bulk that are close together in space, connected by smooth geometry. Regions of the boundary that are not entangled correspond to regions of the bulk that are far apart or even disconnected. One of the key insights came from a physicist named Shinsei Ryu and Tadashi Takayanagi in 2006. They discovered a formula now called the RYRTT formula that relates the entanglement entropy of a region in the boundary theory to the area of a minimal surface in the bulk space-time. Essentially, the amount of entanglement between two regions in the boundary determines the size of the surface that separates them in the bulk. This was revolutionary. It showed that geometry in the bulk is not independent of the quantum state in the boundary. The shape of space, the distances between points, the curvature, all of this depends on how entangled the quantum state is. Change the entanglement pattern and you change the geometry. Think about what this means. We normally think of space as a fixed stage, and quantum fields live in that space and can become entangled or not. But this is saying the opposite. The quantum entanglement comes first, and space is constructed from that entanglement. No entanglement means no space. Strong entanglement means nearby space. Weak entanglement means distant space. This idea has been developed into a research program called IT from Qubit, a play on Wheeler's IT from bit, but updated for quantum information. The idea is that everything, all the ITs of physics, including space itself, emerges from qubits, from quantum information and its entanglement structure. One striking example is the ER equals EPR conjecture proposed by Juan Maldacena and Leonard Susskind in 2013. ER stands for Einstein-Rosen bridges, which is the technical name for wormholes, shortcuts through space-time connecting distant regions. EPR stands for Einstein-Podolsky-Rosen, the names of the physicists who first studied entanglement in a famous paper from 1935. The ER equals EPR conjecture says that these two things, which seem completely different, are actually the same thing viewed from different perspectives. A wormhole connecting two regions of space is exactly the same thing as those regions being quantum entangled. The geometric connection of a wormhole is dual to the information connection of entanglement. This sounds crazy, but it makes sense in the holographic framework. In the boundary theory, two regions are entangled, sharing quantum information. In the bulk, this appears as a geometric connection, a wormhole bridging the regions. The entanglement is the wormhole. They are two descriptions of the same phenomenon. Now, the wormholes in ER equals EPR are not the traversable wormholes of science fiction. You cannot use them to travel faster than light or as shortcuts across the universe. They are quantum wormholes, connections in the entanglement structure. But the point is that geometry and entanglement are not separate things. They are different aspects of the same underlying reality. This leads to an even deeper insight. If entanglement creates space, then the Big Bang, the origin of our universe, can be thought of as the moment when quantum information started organizing itself into an entangled structure. The early universe was a highly entangled quantum state, and as it evolved, that entanglement structure manifested as the expansion of space. The growing universe is really the growing complexity of quantum entanglement relationships. Space is not a container that things happen inside. Space is an emergent phenomenon, a way of describing the pattern of quantum information relationships. Distance is not fundamental. What is fundamental is the connectivity of information, how much quantum entanglement links different parts of the system. This explains something that has always been mysterious. Why is space three-dimensional? Why not 2 dimensions, or 4, or 17? Nobody knows the answer for certain, but in the IT from Qubit picture, the dimensionality of space would depend on the structure of the quantum system. Different patterns of entanglement would give rise to different effective geometries. 3 dimensions might emerge from a particular type of entanglement structure that happens to be stable or natural for some reason we do not yet understand. It also suggests that at the smallest scales, the Planck scale, where quantum gravity effects become important, space might not exist at all as a smooth, continuous thing. Instead, there would just be discrete quantum information, bits or qubits, and what we call space would be an approximation that emerges when you look at large collections of qubits. This is a complete inversion of how we normally think. We usually start with space and time, and then put quantum fields in that space. But the modern view is that we should start with quantum information and then derive space and time from the entanglement structure. Space and time are not fundamental. They are emergent classical approximations to something more fundamental and more quantum. John Wheeler said "it" from bit in the 1980s, before most of these ideas were developed. He was ahead of his time. He saw in the weirdness of quantum mechanics a hint that information was more basic than matter or space. But he could not have imagined how literally true his vision would turn out to be. Today, it from bit has become it from qubit, and we are learning that space itself is woven from quantum information, from the pattern of entanglement between qubits. But even as this picture becomes clearer, there are still deep mysteries. We still do not fully understand the measurement problem in quantum mechanics. We still do not know exactly how classical space emerges from quantum information in detail. And we still have puzzles about black holes that suggest we are missing something important. These mysteries are what physicists are grappling with right now. Before we explore those frontiers, though, let us take a pause. Let us step back and catch our breath. Because we have been climbing a very steep intellectual mountain, and we are about to climb higher. This is a good moment to consolidate, to make sure we understand where we have been and where we are going. Okay, stop for a moment. Take a breath. We have covered a huge amount of material in the last 2 hours. Let us recap where we have been and make sure we are still together. We started with a mystery, the double-slit experiment and quantum weirdness that seemed to involve information in a fundamental way. John Wheeler said, "it from bit," suggesting that information might be what reality is really made of. Most physicists thought this was just philosophy. Then black holes entered the picture. Stephen Hawking discovered that black holes radiate and seem to destroy information. This started a war with Leonard Susskind, who insisted information must be conserved. The war lasted 30 years. The resolution came from holography. Gerard 't Hooft and Susskind proposed that information in a volume is encoded on a boundary surface. Juan Maldacena proved this with ADS-CFT, showing that a gravity theory in bulk space is equivalent to a quantum theory on the boundary. Space emerges from information. Hawking eventually conceded. We then saw that information connects to entropy and thermodynamics. Entropy is missing information. The second law of thermodynamics is about information spreading out. Time might flow in the direction of increasing information dispersal. We learned about quantum information and its weird properties: superposition, entanglement, no cloning. These are not just technical details. They are fundamental features that make quantum information different from classical information. Finally, we saw that space itself emerges from quantum entanglement. The pattern of which qubits are entangled with which other qubits creates the geometry of space-time. More entanglement equals more connection equals less distance. Space is not fundamental. Information is fundamental. That is where we are. We have climbed from quantum weirdness to black holes to holography to the emergence of space itself from information. And the evidence, both mathematical and experimental, supports this picture. Information really does appear to be fundamental to physics. Now, let us be honest about what we know and what we do not know. What we know is that quantum mechanics conserves information. We know that AD-CFT works mathematically. We know that entanglement is real and has been verified experimentally thousands of times. We know that the mathematics of holography is sound. These are established results. What we do not know yet is exactly how this applies to our actual universe. ADS-CFT is about anti-de Sitter space, which is not quite like our universe. We do not have a complete theory of quantum gravity that works in all situations. We do not fully understand how measurement works, or how classical reality emerges from quantum reality. We have the outline of the picture, but many details are still being filled in. We are also venturing into areas that are hard to test experimentally. We cannot create black holes in laboratories. We cannot directly probe the Planck scale where quantum gravity effects are important. We cannot see the holographic boundary of the universe if one exists. So some of these ideas are still theoretical, supported by mathematics and consistency arguments, but not yet by direct experimental tests. That said, the progress over the last 50 years has been extraordinary. Ideas that seemed like wild speculation in the 1980s are now mainstream physics. The holographic principle, once considered too radical, is now taught in graduate courses. ADS-CFT is one of the most active areas of research. Quantum information theory has gone from a niche topic to a central pillar of theoretical physics. We are living through a genuine paradigm shift in how physics understands reality. And that shift is toward seeing information as fundamental. We are moving from a physics based on particles and forces and space to a physics based on information and entanglement and emergence. So where do we go from here? In the next hour, we are going to explore three things. First, we will look at the paradoxes and problems that still remain, the puzzles that tell us we do not understand everything yet. Second, we will look at experimental efforts to test these ideas and what we've learned so far. Third, we will explore the implications of all this for how we understand reality, including some speculative but fascinating ideas about consciousness, the nature of time, and the future of physics. You have made it this far. You have climbed the mountain and seen the view from up high. Now we are going to explore the frontier, the cutting edge where physics is still being discovered, where questions outnumber answers, where wonder and mystery remain. This is where science gets exciting. This is where we see how much we have learned and how much we still have to learn. Just when physicists thought they had figured out how black holes preserve information, how holography works, how space emerges from entanglement, a new set of paradoxes appeared. These paradoxes show that even with all our progress, we still do not fully understand the relationship between quantum mechanics and gravity. We still do not completely understand how information behaves near black holes. But these paradoxes are not failures. They are clues. They are nature's way of telling us that we are still missing something, that there is something deeper waiting to be discovered. Every time physics encounters a paradox, a situation where two well-established principles seem to contradict each other, it signals an opportunity for a breakthrough. The three paradoxes we are about to explore, the firewall paradox, the measurement problem, and the cosmological information problem, are the frontiers of modern physics. They are the puzzles that physicists are actively working on right now, and solving them might lead to the next great revolution in our understanding of information and reality. Chapter 13. The Information Paradoxes. The first paradox is called the firewall paradox, and it emerged in 2012, long after most physicists thought the black hole information problem was solved. A group of physicists, including Ahmed Almhairi, Donald Marolf, Joseph Polchinski, and James Sully, published a paper that shook up the field. They showed that preserving information in black hole evaporation leads to a contradiction with Einstein's equivalence principle. Here is the problem. Suppose a black hole forms and then slowly evaporates through Hawking radiation. For information to be conserved, the radiation coming out late in the evaporation must be entangled with the radiation that came out early. The late radiation has to carry information about what fell in, and that information is encoded in correlations with the early radiation. This is how information escapes, through subtle quantum correlations in the Hawking radiation. But there is a second requirement. The radiation at the horizon, the place where it is being generated, must also be entangled with particles falling into the black hole. This is required by Einstein's equivalence principle, which says that if you are freely falling across the event horizon, you should not notice anything special. The horizon should be a smooth place, not violent or discontinuous. And for that smoothness to hold quantum mechanically, there must be strong entanglement across the horizon. Here is the paradox. A quantum system can only be strongly entangled with one other system at a time. This is called monogamy of entanglement. If particle A is maximally entangled with particle B, it cannot also be maximally entangled with particle C. Entanglement is exclusive. So the late Hawking radiation cannot be both entangled with early radiation, as required for information conservation, and entangled with the interior of the black hole, as required by smoothness of the horizon. One or the other has to give. If you give up the entanglement with early radiation, information is not conserved, violating quantum mechanics. If you give up the entanglement with the interior, the horizon becomes a place of extremely high energy density, a firewall that would incinerate anything trying to cross it. This violates the equivalence principle and changes the basic nature of black holes. Neither option is acceptable. So we have a genuine paradox. Something in our understanding must be wrong, but nobody knows what. This paradox is still being debated today. Different physicists propose different solutions, but there is no consensus yet. The firewall paradox tells us that we still do not understand how information escapes from black holes in detail. We know it must escape, but the mechanism is subtle, and we have not figured it out completely. The second paradox is older and more fundamental. It is called the measurement problem in quantum mechanics, and it has been troubling physicists since the early days of quantum theory in the 1920s. Here is the problem. Quantum mechanics describes systems as being in superpositions of multiple states. An electron can be spin up and spin down simultaneously. A photon can be in multiple places at once. The mathematics of quantum mechanics, the Schrödinger equation, describes smooth evolution of these superpositions over time. And that evolution is unitary. It preserves information perfectly. No information is lost as a quantum state evolves. But when you measure a quantum system, something different happens. The superposition collapses to a single definite outcome. You measure the electron and find it either up or down, not both. You detect the photon at one location, not multiple. The smooth unitary evolution suddenly becomes a discontinuous jump to a specific state. This is weird for two reasons. First, the collapse is not unitary. If you start with a superposition of many possibilities and end with one definite outcome, you have lost information about the other possibilities. That seems to violate information conservation. Second, the collapse is mysterious. When exactly does it happen? What counts as a measurement? Does it require a conscious observer, or is any interaction enough? The mathematics of quantum mechanics does not tell us. This is the measurement problem. If quantum mechanics is supposed to describe everything, it should describe measurement too. But the collapse of the wave function does not follow from the Schrödinger equation. It seems to be an additional postulate, something added to the theory without clear justification. Many interpretations of quantum mechanics have been proposed to solve this problem. The Copenhagen interpretation says that measurement is fundamentally different from regular evolution, and we should not ask about what happens during collapse. The many worlds interpretation says that all outcomes happen, the universe splits into branches, and we just see one branch. The de Broglie bomb theory adds hidden variables that determine outcomes. There are dozens of other proposals, but none of these interpretations are universally accepted, and the measurement problem remains unsolved. And it matters for information because we do not understand how information transitions from being quantum and in superposition to being classical and definite. We do not understand how the world we observe, with its definite facts and specific outcomes, emerges from the quantum realm of superpositions and possibilities. This is directly relevant to black holes and holography. When information falls into a black hole and then comes back out in Hawking radiation, how does it go from being quantum information in the interior to being encoded in outgoing radiation that we can measure? The process involves something like measurement, a transition from quantum to classical, and we do not fully understand how that works while preserving information. The third paradox is more speculative but very important for cosmology. It is called the cosmological information problem, and it is about what happens to information in an expanding universe like ours. Our universe is expanding, and the expansion is accelerating. This means that distant regions of space are moving away from us faster and faster. Eventually, they move away so fast that light from those regions can never reach us. They pass beyond our cosmic horizon, the boundary of what we can ever observe. So here is the question. When information passes beyond our cosmic horizon, is it gone forever? Is it destroyed from our perspective, or does it somehow remain accessible? This is similar to the black hole information paradox, but in reverse. With a black hole, information falls in, and we worry about whether it comes back out. With cosmic horizons, information gets pushed away by expansion, and we worry about whether we have lost it permanently. Some physicists think this is not a problem. They say that from our perspective, the information is indeed lost. But that is okay, because the information still exists somewhere in the universe, just beyond our horizon. Other physicists think this suggests that information might be encoded holographically on our cosmic horizon, similar to how information is encoded on black hole horizons. There is even speculation that our entire observable universe might be holographic, with all the information about the interior encoded on a boundary at the cosmic horizon. This would make our universe literally a hologram, in the same sense that ADS space is holographic in ADS CFT. These ideas are very speculative because we do not have a theory of quantum gravity that fully works in our type of universe, called de Sitter space. ADS CFT does not directly apply to de Sitter space, so we cannot use it to answer these cosmological questions definitively. This is an active area of research, and many fundamental questions remain open. These three paradoxes, the firewall, the measurement problem, and the cosmological information problem, show us where the boundaries of current understanding lie. They are the places where we still need new insights, new mathematics, maybe even new principles that we have not thought of yet. They remind us that even though we have learned a tremendous amount about information and physics, we are not done. There is still mystery, still wonder, still discovery waiting. But we should not despair at these unsolved problems. We should celebrate them, because paradoxes are opportunities. Every major breakthrough in physics has come from confronting a paradox, a place where the old ideas do not quite work, and finding a new way to think that resolves the contradiction. The paradoxes we face now are signposts pointing toward future breakthroughs, and we are not just theorizing in a vacuum. Physicists are doing experiments, building technologies, testing these ideas in whatever ways they can. And some of those tests are already bearing fruit. Let us see what we have learned from actual experiments. We have spent a lot of time on theory, on thought experiments, on mathematics and arguments about what must be true. But physics is ultimately an experimental science. Theories need to be tested. Ideas need to be confronted with reality. So the question arises, can we actually test any of these ideas about information being fundamental? Can we verify quantum entanglement? Can we probe the limits of information storage? Can we simulate black holes in laboratories? The answer is yes, at least partially. While we cannot yet test some of the most extreme predictions about quantum gravity and the Planck scale, we can test many aspects of quantum information theory, and the results have been spectacular. Over the last few decades, physicists have done experiments that would have seemed like magic just 50 years ago. Experiments that prove quantum entanglement is real, that demonstrate quantum computing, that probe the thermodynamics of information. This is the story of how theory meets experiment in the age of quantum information. Chapter 14. Testing Information Physics. Let us start with quantum entanglement, that spooky action at a distance that Einstein doubted was real. For decades after Einstein and others first pointed out how weird entanglement was, nobody knew how to decisively test whether quantum mechanics was right about it, or whether there might be some classical explanation. Then, in 1964, a physicist named John Bell came up with a brilliant idea. Bell showed that quantum entanglement makes predictions that are different from any theory based on classical local interactions. He devised an inequality, now called Bell's inequality, which sets a limit on how correlated two measurements can be if they are independent and determined by local hidden variables. Quantum mechanics violates Bell's inequality. The quantum predictions exceed Bell's bound. So, if you do the experiment and measure the correlations between entangled particles, you can test whether reality is quantum or classical at this fundamental level. The first tests were done in the 1970s and 80s by physicists like John Clauser, Alain Aspect, and others. They created entangled photons, sent them to different detectors, measured their properties, and calculated the correlations. And the results were clear. Bell's inequality is violated. The correlations are stronger than any classical theory allows. Quantum entanglement is real. These experiments have been refined and repeated thousands of times. The most sophisticated versions close all possible loopholes, ensuring that the measurements are truly independent and that no classical communication could explain the results. Every test confirms quantum mechanics. Entanglement is not an illusion or an artifact of imprecise calculations. It is a real feature of nature. This is crucial for our story because entanglement is the key to how space emerges from information. The experimental verification of entanglement gives us confidence that the quantum information framework is correct. When we say space emerges from entanglement patterns, we are not just speculating. We are building on experimentally verified phenomena. Another major experimental development is quantum computing. Quantum computers are machines that manipulate quantum information directly, using qubits in superposition and entanglement to perform calculations. This is not just theoretical anymore. Quantum computers exist and they work. Companies like Google, IBM, IonQ, Rigetti and many others have built quantum computers with dozens to hundreds of qubits. In 2019, Google announced quantum supremacy, showing that their quantum computer could solve a specific problem in minutes that would take a classical computer thousands of years. This was a landmark demonstration that quantum information processing is not just possible, but can be more powerful than classical processing. Now, quantum computers are still in their early stages. They are noisy, error-prone, limited in size. We cannot yet build the large-scale fault-tolerant quantum computers needed for many applications. But progress is rapid. Error correction techniques are improving, qubit quality is increasing. Every year, quantum computers get better. Why does this matter for fundamental physics? Because quantum computers are laboratories for studying quantum information directly. They let us create complex entangled states, manipulate quantum information in controlled ways, test the principles of quantum mechanics, and explore the limits of information processing. They are experimental platforms for information physics. Some physicists are even using quantum computers to simulate quantum field theories and black hole physics. You can create a simplified model of a black hole in a quantum computer, watch it evolve, see information scramble, and then potentially unscramble, and test predictions about how information behaves in strongly interacting quantum systems. These simulations are not the same as real black holes, but they let us study the quantum information dynamics in regimes that are otherwise inaccessible. Another experimental frontier involves what are called analog black holes, or black hole analogues. These are systems in the laboratory that mimic some features of black holes. For example, you can create a flow of fluid or sound where the flow velocity exceeds the speed of sound waves, creating an acoustic horizon. Sound waves cannot escape from inside this horizon, just like light cannot escape from inside a black hole event horizon. Physicists have created these analog black holes and looked for analog Hawking radiation, the emission of sound waves from the acoustic horizon. And they found it. The analog Hawking effect is real. This gives us experimental evidence that Hawking's original calculation, the one that started the information wars, was correct about the basic physics. Black holes really do radiate. Of course, acoustic black holes are not the same as gravitational black holes. They cannot tell us directly about information loss or holography. But they give us confidence that the basic phenomenon of horizon radiation is correct, and they let us test quantum effects in curved space-time in a controlled laboratory setting. There are also experiments testing the thermodynamics of information, Landauer's principle that erasing information costs energy. These experiments use tiny systems, sometimes single electrons or small molecules, and they measure the energy dissipated when information is erased. The results confirm Landauer's principle. Erasing information really does have a thermodynamic cost. Information is physical. More ambitiously, some experiments are trying to probe quantum gravity effects, the regime where both quantum mechanics and gravity are important. This is incredibly difficult because quantum gravity effects are only significant at the Planck scale, which is far too small to reach with current technology. But there are indirect approaches. For example, some experiments look for tiny violations of known symmetries that might arise from quantum gravity. Others try to detect gravitational effects of quantum superpositions, testing whether gravity responds to quantum states in the expected way. So far, no deviations from standard quantum mechanics and general relativity have been found, but the search continues. The overall picture from experiments is encouraging. Every testable prediction of quantum mechanics and quantum information theory has been confirmed. Entanglement is real. Quantum computing works. Analog systems behave as predicted. Information has thermodynamic costs. The framework we have been discussing is not just theoretical speculation. It is grounded in experimental reality, where we can test it. Of course, many aspects of the holographic principle and emergent space-time cannot be tested directly with current technology. We cannot probe the Planck scale. We cannot create real black holes. We cannot observe the holographic boundary of the universe if it exists. These ideas are supported by mathematical consistency, by the success of ADS-CFT, by the resolution of the information paradox, but not yet by direct experimental tests. This is the nature of fundamental physics at the frontier. Theory sometimes gets ahead of experiment. Physicists develop mathematical frameworks that seem beautiful and consistent and that solve problems, and they have confidence in these frameworks even before every prediction can be tested. But experiment always has the final say. If future experiments contradict holography or emergent space-time, physicists will have to revise their ideas. For now, though, the experimental evidence supports the quantum information view of physics. Everything we can test works as predicted. And that gives us confidence to explore the implications of this framework, even the more speculative ideas that extend beyond what we can currently test. Which brings us to one of the most controversial and fascinating questions. What does information physics tell us about consciousness? We are about to venture into controversial territory. Everything we have discussed so far, black holes, holography, quantum entanglement, emergent space-time, these are ideas that most physicists working in the field would agree on, at least in broad outline. But now we are going to ask about consciousness, and that is where things get much more speculative and much less clear. Does information physics tell us anything about consciousness? Is consciousness itself related to quantum information, to information integration, to measurement in quantum mechanics? Or is consciousness a separate phenomenon that happens to involve information processing, but is not fundamentally connected to the physics we have been discussing? Honest answer, we do not know. Consciousness is deeply mysterious. We do not have a complete scientific theory of how subjective experience arises from physical processes. Different scientists have very different views on this question. Some think consciousness will eventually be explained in terms of information processing and quantum mechanics. Others think consciousness is something separate that physics alone cannot explain. What I can do is tell you about the connections that some people see, the speculations that serious researchers have made, and the limits of what we currently understand. This is the most uncertain part of our journey, but it is also fascinating. So let us explore what might connect information, quantum mechanics, and consciousness. Chapter 15. The Observer Problem. The measurement problem in quantum mechanics has a peculiar feature that has puzzled physicists from the very beginning. The collapse of the wave function, the transition from quantum superposition to definite outcome, seems to involve an observer. Something about observation or measurement causes the quantum system to choose one outcome from many possibilities. This has led some people to wonder, does consciousness play a role in quantum mechanics? Does the act of conscious observation cause wave function collapse? This was suggested by some of the founders of quantum mechanics, including Eugene Wigner and John von Neumann. They thought that perhaps consciousness was the special ingredient that makes measurement different from regular physical interactions. But most physicists today do not believe consciousness is necessary for measurement. A measuring device does not need to be conscious to cause wave function collapse. A detector, a piece of film, even a dust particle interacting with a quantum system can cause decoherence, the spreading out of quantum information into the environment, which effectively collapses the wave function from our perspective. So consciousness is probably not required for quantum measurement. But that does not mean consciousness has nothing to do with quantum information. There might still be connections, just more subtle ones. One idea that has gained attention is integrated information theory, or IIT, proposed by neuroscientist Giulio Tononi. IIT is an attempt to build a mathematical theory of consciousness based on information. The basic idea is that consciousness is identical to integrated information that is irreducibly combined across a system. Let me explain what that means. When you have information in separate independent parts, like two computer chips that do not talk to each other, the information is not integrated. You could analyze each chip separately, but when parts of a system are connected and interdependent, when what happens in one part depends on what happens in other parts, then the information is integrated. The system has to be understood as a whole, not as separate pieces. According to IIT, the amount of integrated information in a system, measured by a quantity called phi, determines the level of consciousness of that system. More integrated information means more consciousness. A system with no integrated information, where all the parts are independent, has no consciousness. A system with highly integrated information has rich conscious experience. IIT makes some striking predictions. It suggests that consciousness is not all or nothing, but comes in degrees. It suggests that consciousness is substrate independent, meaning it depends on the pattern of information integration, not on what physical material the system is made of. So, in principle, an artificial system could be conscious if it has the right information structure. It also suggests that some simple systems might have small amounts of consciousness if they have any integrated information at all. This is sometimes called panpsychism, the idea that consciousness is a fundamental feature of systems with integrated information, not something that magically appears only in complex brains. Now, IIT is controversial. Many neuroscientists and philosophers question whether it really captures what consciousness is. Does high integrated information really equal consciousness, or is that just a correlation? Can you have consciousness without information integration? Can you have information integration without consciousness? These are open questions. But IIT is interesting for our purposes because it connects consciousness to information in a fundamental way. It suggests that consciousness is not some magical substance separate from physics. It is a property of certain information structures. And if information is fundamental to physics, as we have been arguing, then consciousness might be deeply connected to the fundamental nature of reality. There is also speculation about quantum effects in the brain. Some researchers, most notably Roger Penrose and Stuart Hameroff, have suggested that consciousness involves quantum processes in microtubules, structural elements inside neurons. They propose that quantum coherence in these structures plays a role in how consciousness arises, and that the collapse of quantum states in the brain is related to moments of conscious experience. This is highly speculative, and most neuroscientists are skeptical. The brain seems too warm and noisy for delicate quantum coherence to survive for meaningful amounts of time. Decoherence would destroy quantum effects almost instantly in such an environment. But the proposal is out there, and some research is exploring whether quantum effects might play any role in neural processing. Here is where I need to be very clear about the boundaries between what we know and what we speculate. We know that brains process information. We know that information processing in the brain involves complex patterns of neural activity. We know that consciousness somehow emerges from this neural activity. What we do not know is whether consciousness is simply the result of classical information processing, or whether quantum information plays any essential role. We also do not know whether consciousness is just information processing, or whether there is something more to conscious experience that goes beyond information. This is called the hard problem of consciousness, posed by philosopher David Chalmers. The hard problem is explaining why information processing feels like something from the inside. Why is there subjective experience at all? Why does seeing red feel like something rather than just being information processing without any felt quality? Information physics can explain a lot about the structure of consciousness, about what kinds of information can be processed, about how information integrates in neural networks. But whether it can explain the feel of consciousness, the subjective quality of experience, that is unclear. Some people think eventually we will explain this in information terms. Others think subjective experience is something fundamentally different that will never be reduced to information processing. My personal view, which you should take as speculation not established fact, is that if information is truly fundamental to physics, and if space and time and matter all emerge from information structures, then consciousness probably also emerges from information patterns. Consciousness might be what it feels like from the inside when information reaches a certain level of integration and complexity. But I cannot prove this, and many smart people disagree. What I can say with more confidence is that the measurement problem in quantum mechanics and the hard problem of consciousness might be related. Both involve a transition from potentiality to actuality, from many possibilities to one definite outcome, from the quantum realm to the classical world of our experience. Understanding how measurement works in quantum mechanics might shed light on how conscious experience arises, or vice versa. They might be two aspects of the same underlying mystery about how definite classical reality emerges from quantum information. But we are far from solving either problem. The relationship between consciousness and quantum information remains one of the great mysteries at the boundary of physics, neuroscience, and philosophy. It is an area where we need more research, more careful thinking, and probably some new insights that we have not had yet. So let us be humble here. We have learned an enormous amount about information and physics. We know information is conserved. We know space emerges from entanglement. We know quantum information has special properties, but we do not know how or whether this connects to consciousness in a deep way. This is the frontier where knowledge blurs into speculation, and we must be honest about the difference. Now let us pull back from this speculative edge and talk about things we understand better. Let us talk about the implications of information physics for how we understand the universe, for technology, for the future of physics. These implications are profound, even without invoking consciousness, and they give us a new way to think about everything from time to complexity to the nature of reality itself. We have established that information appears to be fundamental to physics. We have seen the evidence from black holes, from holography, from quantum mechanics, from the emergence of space itself. We have explored the paradoxes that remain and the experimental tests that confirm our understanding. Now it is time to ask, what does all of this mean? What are the implications of living in a universe where information is fundamental? The implications cascade outward in every direction. They change how we think about the universe as a whole. They change how we understand time and causality. They change what is possible and what is impossible. They open up new technologies and new ways of thinking about complexity and life. This is not just an abstract theoretical shift. This is a change in our entire worldview about what reality is and how it works. Let us explore what it means to live in an information-based universe. Chapter 16, What This Means for Reality. If information is fundamental, the first and most obvious implication is that the universe can be thought of as a kind of computer. Not a computer in the sense of a machine built by engineers with transistors and wires, but a computer in the abstract sense of a system that processes information according to rules. Every physical process is an information process. When particles interact, they are exchanging information. When fields propagate through space, they are transmitting information. When systems evolve in time, they are computing their future states from their present states according to the laws of physics. The laws of physics themselves are rules for information processing. This is sometimes called the computational universe idea, and it has been developed by physicists like Ed Fredkin, Stephen Wolfram, and Seth Lloyd. The universe is computing itself. Every particle, every field, every interaction is part of a vast distributed computation. And what we call reality is the output of that computation. This does not mean we live in a computer simulation created by some advanced civilization, though some people have speculated about that. What it means is that at the most fundamental level, the activity of the universe is information transformation. The stuff of reality is information, and the dynamics of reality is computation. This has a strange but beautiful implication. It means that everything that happens in the universe is, in a sense, necessary. Not predetermined by fate or divine plan, but necessary as the output of information processing given the inputs and the rules. The universe is solving a vast equation, and what we experience is the solution unfolding. Another implication concerns the nature of time. We normally think of time as something that flows, something independent and fundamental that everything else moves through. But in an information-based universe, time might be about the accumulation of information. Think about it this way. The past is fixed because information about past events is stored in the present state of the universe. Every particle, every field, every configuration of matter and energy carries information about what happened before. The past is frozen into present information structures. That is why we can remember the past, why we have fossils and photographs and historical records. The past left information traces in the present. The future, by contrast, is not yet determined in the same way. Information about future events does not exist in the present. There are many possible futures consistent with the present state and the laws of physics. As time moves forward, new information is generated, new outcomes are determined, and the range of possibilities narrows. The future becomes the present, which then becomes the past as information accumulates. So the arrow of time, the directionality from past to future, might be fundamentally about the direction of increasing information. Time flows in the direction where information accumulates, where more and more facts become definite, where the uncertainty of the future crystallizes into the certainty of the past. This connects back to entropy and the second law of thermodynamics. Remember that entropy increases over time, and entropy is missing information that has spread out into inaccessible places. So the second law is saying that accessible information decreases over time, or equivalently, that total information stays constant but gets more and more scrambled and harder to read. Time might be, at its deepest level, about the flow of information from accessible to inaccessible, from ordered to disordered, from concentrated to dispersed. The universe is not moving through time. Time is the accumulation and dispersal of information. A third implication is that there are limits to what can be known, even in principle. If information storage is limited by the holographic principle, if the maximum information in a region is proportional to the surface area of its boundary, then there is a maximum amount of knowledge that can exist about any system. You cannot know everything about everything because there is not enough room in the universe to store that much information. Knowledge itself is bounded. This is not just a practical limitation. This is fundamental. The universe contains a finite amount of information, and that sets absolute limits on what can be known or computed. This also means there are limits to computation and intelligence. Even the most advanced possible computer, even a computer the size of the observable universe, could only store and process a finite amount of information. There are questions it could not answer, problems it could not solve, simply because they require more information than can physically exist. This is both humbling and liberating. It is humbling because it means our knowledge will always be incomplete. There will always be things we cannot know, not because we are not smart enough or do not have good enough instruments, but because the information does not exist. It is liberating because it means we are not failing when we encounter limits. We are encountering the fundamental structure of reality. A fourth implication concerns emergence and complexity. If simple information processing rules can give rise to space-time, to matter, to forces, then complex structures can emerge from simple rules. This is something we see everywhere in nature. Simple rules of chemistry give rise to complex molecules. Simple rules of genetics give rise to the enormous diversity of life. Simple rules of neural dynamics give rise to intelligence and behavior. Information physics gives us a framework for understanding emergence. Complex structures are patterns of information organization. They emerge when information is processed in certain ways, when feedback loops form, when information integrates across scales. Life itself can be understood as information that has learned to preserve and replicate itself. Evolution is optimization of information structures for survival and reproduction. This does not reduce life or consciousness or human culture to simple computations. Emergence means that new properties appear at higher levels of organization that are not obvious from the lower levels. But it does suggest that there is continuity from the simplest physical processes to the most complex phenomena. It is all information processing at different scales with different structures. Understanding this might lead to new approaches in biology, neuroscience, economics, ecology, anywhere that complex systems arise from simpler components. Information theory becomes a universal language for describing how simple things combine to make complex things. Chapter 17. Technology and the Future. The information physics framework is not just changing our understanding of reality. It is also driving new technologies that would have seemed impossible just a few decades ago. And these technologies, in turn, are helping us probe fundamental questions about information and the limits of what is possible. The most obvious technology is quantum computing, which we mentioned earlier. Quantum computers exploit the unique properties of quantum information: superposition, entanglement, interference. They can solve certain problems exponentially faster than classical computers. Problems like factoring large numbers, simulating quantum systems, optimizing complex functions, searching databases. All of these can be done more efficiently with quantum information processing. As quantum computers improve, they will enable things that are currently impossible. Simulating molecules and materials for drug discovery and materials science. Breaking current encryption systems while enabling new unbreakable quantum cryptography. Solving optimization problems in logistics and machine learning. Perhaps even helping us understand quantum gravity by simulating toy models of holographic space-time. Related to quantum computing is quantum communication and quantum cryptography. These technologies use entanglement to transmit information in ways that are fundamentally secure. Any attempt to eavesdrop on a quantum communication channel disturbs the quantum states and can be detected. This enables perfectly secure communication guaranteed by the laws of physics, not just by mathematical difficulty. China has already launched quantum communication satellites. Quantum networks are being built connecting cities with quantum encrypted links. In the future, we might have a quantum internet where information is transmitted securely using entangled photons, protected by the no-cloning theorem and the measurement disturbance principle. Another implication of information physics is better understanding of thermodynamics and energy efficiency. Landauer's principle tells us that erasing information has an energy cost. This sets a fundamental limit on how efficient any computer can be. But it also suggests ways to approach that limit by designing computers that minimize information erasure, that do reversible computation where possible. There has been research into reversible computing, where computations are done in ways that preserve information rather than erasing it. In principle, you could do computation with arbitrarily little energy dissipation if you never erase information. In practice, this is very difficult because you need to keep track of all the information, all the intermediate states, and that requires memory. But understanding these fundamental limits helps us design more efficient systems. Information theory also illuminates the limits of engine efficiency, not just computer efficiency. The maximum efficiency of a heat engine is fundamentally related to the information content and entropy flow between hot and cold reservoirs. Understanding this at a deep level might lead to better designs for power generation, cooling systems, any technology that involves energy conversion. Looking further into the future, information physics might lead to new approaches to artificial intelligence. If intelligence is really about information processing, and if we understand the principles of how information integrates and processes at a fundamental level, we might be able to build more intelligent systems. We might understand what makes certain information structures more effective at learning, reasoning, and problem-solving. There is also speculation about whether quantum effects could be exploited in AI, whether quantum machine learning might be more powerful than classical machine learning. This is still very early research, but there are hints that quantum systems can learn patterns in data more efficiently than classical systems in some cases. On an even more speculative level, if space emerges from entanglement as we discussed, understanding this might someday lead to technologies that manipulate space-time itself. If we could control entanglement patterns at a fundamental level, could we create shortcuts through space, wormholes, warped geometries? This is pure science fiction for now, but it is the kind of thing that information physics makes conceivable, at least in principle. More realistically, understanding information limits helps us understand what is impossible, and that is valuable too. It tells us not to waste time trying to build perpetual motion machines or perfectly efficient engines or computers that solve uncomputable problems. There are fundamental limits, and understanding them helps us focus on what is actually achievable. The long-term trajectory of technology, if the information physics framework is correct, is toward deeper and deeper manipulation of information at more fundamental levels. We started with mechanical information processing, gears, levers, abacuses, then electrical, switches, transistors, integrated circuits, then quantum, qubits, entanglement, quantum gates. Perhaps someday we will reach the Planck scale, directly manipulating the fundamental qubits that space-time emerges from. That would be the ultimate technology, the ability to program reality itself at the information level. But that is far in the future, if it is possible at all. For now, the practical implications are already profound. Quantum technologies are real and growing. Information theory is being applied across science and engineering. And our understanding of fundamental limits is shaping how we think about what is possible. The information revolution in physics is also an information revolution in technology. And that revolution is just beginning. We are approaching the end of our journey, but we are not quite done yet. Because we have reached the edge of human knowledge, the frontier where what we know fades into what we do not know yet. This is the most exciting place in science. This is where the questions are bigger than the answers, where mystery still reigns, where the next great discoveries are waiting. What we have covered so far is the established framework, the ideas that most physicists working on quantum gravity and information physics would agree with in broad outline. But now we need to talk about the open questions, the problems we are still working on, the directions where research is heading. These are the live issues being debated in physics departments and at conferences right now. If you are a young person thinking about going into physics, these are the problems you might help solve. If you are just curious about how science progresses, this shows you what the cutting edge looks like. Either way, this is where science is most alive, most uncertain, most full of possibility. Let us explore the frontiers of information physics. Chapter 18: What we still don't know. The first major open question is quantum gravity itself. We know that quantum mechanics and general relativity are both correct in their domains, but we do not have a complete theory that unifies them. We do not know how to describe space-time at the Planck scale, where both quantum effects and gravitational effects are strong. There are several approaches to quantum gravity being pursued. String theory is probably the most developed. String theory says that fundamental particles are actually tiny vibrating strings, and different vibration modes correspond to different particles. String theory requires extra dimensions beyond the 3 space and 1 time dimension we experience. Those extra dimensions are supposedly curled up very small, too small to detect. String theory has been very fruitful mathematically. ADS-CFT came from string theory. Much of our understanding of holography comes from string theory. But string theory has not yet made testable predictions that differentiate it from other theories. We cannot directly detect strings because they are far too small. So string theory remains a promising but unproven approach. Another approach is loop quantum gravity. This theory tries to quantize space-time itself, treating space as made of discrete loops and networks rather than smooth continuum. In loop quantum gravity, space has a fundamental granularity at the Planck scale. Area and volume come in minimal quanta, tiny fundamental units. Loop quantum gravity makes different assumptions than string theory and leads to different mathematics. It does not require extra dimensions, but it also has not connected to the holographic principle as clearly as string theory has. It is harder to see how information and entropy work in loop quantum gravity. There are also other approaches. Causal dynamical triangulations tries to build space-time from simple building blocks. Asymptotic safety tries to show that gravity is quantum mechanically consistent without needing strings. Emergent gravity tries to derive gravitational effects from thermodynamic properties of space-time. The honest truth is, we do not know which approach, if any, is correct. We might need ideas from multiple approaches. Or we might need some completely new insight that nobody has had yet. Quantum gravity is the holy grail of theoretical physics, and we are still searching for it. Closely related is the question of initial conditions. Why did the universe start with low entropy? Why did it begin in the particular state it did? The Big Bang was a configuration of extraordinarily low entropy, highly ordered, highly special. Most random configurations would have much higher entropy. So why did the universe start in such an improbable state? This is sometimes called the problem of the past hypothesis, or the problem of cosmological initial conditions. And we do not have a good answer. Maybe there is some principle that selects for low entropy initial states. Maybe our universe is part of a multiverse and we are in a low entropy region just by chance. Maybe time itself emerged at the Big Bang and there is no meaning to asking about before. We simply do not know. From an information perspective, the low entropy initial state means the early universe contained very little information in some sense. The microwave background radiation, the oldest light in the universe, contains very little information compared to what the universe contains now. As the universe evolved, structure formed, galaxies, stars, planets, life, information accumulated, entropy increased. But where did the capacity for this evolution come from? Why were the initial conditions so special? A related mystery is dark matter and dark energy. Observations tell us that ordinary matter, the stuff made of atoms, makes up only about 5% of the universe. About 27% is dark matter, something that has gravity but does not emit light and has not been directly detected. About 68% is dark energy, something causing the expansion of the universe to accelerate. We have no idea what dark matter or dark energy actually are in terms of fundamental physics. We know they exist because of their gravitational effects, but we do not know what they are made of or how they fit into the information physics framework. Do they have information content? Are they related to quantum entanglement in some way? We simply do not know yet. Another deep question is the full nature of the quantum to classical transition. We know that quantum systems exist in superpositions and exhibit entanglement. We know that when we make measurements, we see definite outcomes. But we do not fully understand the mechanism that makes quantum systems appear classical at large scales. The standard answer is decoherence. When a quantum system interacts with a large environment, the environment measures the system, entangling with it and spreading the quantum information into countless degrees of freedom. This makes the superposition effectively impossible to observe from outside. The system appears to have collapsed to a definite state, even though information is conserved and spread into the environment. Decoherence explains a lot, but it does not explain everything. It does not fully answer why we see one particular outcome rather than another. It does not explain the subjective experience of observing a definite result. It is a step towards solving the measurement problem, but it is not the complete solution. Understanding the quantum to classical transition is essential for understanding how the information universe we have been describing connects to the classical world we experience. How do definite facts emerge from quantum possibilities? How does the information encoded in quantum entanglement manifest as the objects and events we see? This is still an active area of research. There is also the question of how exactly space emerges from entanglement in our universe. We have a proof that it works in anti-de Sitter space through ADS-CFT. But our universe is not anti-de Sitter space. Our universe appears to have positive cosmological constant or be approximately flat. Physicists do not yet have a holographic description of our actual universe. There are efforts to extend holography to more realistic cosmologies, to understand whether there is a holographic boundary for our universe and what the boundary theory would be. But this is work in progress. We know holography works in principle, but we do not know all the details for our specific universe. Finally, there is the question of whether information is truly fundamental or whether there is something even deeper. Maybe information itself emerges from something more primitive. Maybe there are principles we have not discovered yet that underlie information. Maybe the ultimate description of reality is not in terms of qubits and entanglement, but in terms of something we do not even have words for yet. This is the nature of science. Every answer opens new questions. Every layer we peel back reveals another layer beneath. We have come an enormous distance in understanding that information is fundamental. But there is no reason to think we have reached the absolute bottom, the final theory of everything. These open questions are not failures. They are opportunities. They are invitations to the next generation of physicists to push further, to discover more, to reveal deeper truths. The frontier is where science happens. And we are living at a frontier moment in the history of physics. But even with all these open questions, even with all the mystery that remains, we have learned something profound. We have learned enough to see the outline of a new worldview, a new way of understanding reality. And that is what we need to synthesize now as we bring our journey to a close. We have travelled a long way together, from quantum weirdness to black holes to holography to emergent space-time, from abstract mathematics to concrete experiments, from well-established facts to speculative frontiers. Now it is time to bring it all together, to see the big picture, to understand what we have really learned about information and reality. This is not just about physics. This is about how we understand the universe we live in, what it is made of, how it works, why it is the way it is. We have witnessed a paradigm shift, a change in the basic framework scientists use to think about nature. And that shift is toward information. Let us synthesize everything we have learned into a coherent picture of reality. Chapter 19. The Big Picture. Let us trace the full arc of our journey to see how all the pieces fit together. We began with the strangeness of quantum mechanics. The double-slit experiment showed us that particles behave differently depending on whether information about their path exists. This was our first hint that information plays an active role in determining what happens, not just a passive role in describing it. John Wheeler saw this and coined the phrase "it from bit," suggesting that physical reality emerges from information. Then black holes entered the story. Stephen Hawking discovered that black holes radiate and appeared to destroy information. This violated the fundamental principle of quantum mechanics that information is conserved. Leonard Susskind insisted this could not be right, that information must be preserved somehow. This started the black hole wars, a decades-long debate about whether information is truly fundamental. The resolution came from holography. Gerard, 't Hooft and Susskind proposed that information in a volume of space is actually encoded on the boundary surface. This seemed impossible at first, but Juan Maldacena proved it with ADS-CFT, showing an exact correspondence between a gravity theory in bulk space and a quantum theory on the boundary. Space itself emerges from information encoded on a lower dimensional surface. This meant that black holes do preserve information. The information is not hidden inside the volume. It is encoded on the event horizon. When the black hole evaporates, the information comes back out in the Hawking radiation, scrambled but not destroyed. Hawking eventually conceded, admitting that information is conserved. Quantum mechanics was safe. We then explored the deep connection between information and entropy. Entropy is missing information, information that has become inaccessible. The second law of thermodynamics, that entropy increases, is really a statement about information spreading out and becoming harder to recover. Time itself might be fundamentally about the flow of information from accessible to inaccessible states. We learned about quantum information and its unique properties. Qubits can exist in superposition, being in multiple states simultaneously. Particles can be entangled, sharing information in ways that violate classical limits. Quantum information cannot be cloned, making it more physical and more fragile than classical information. These properties are not just curiosities, they are fundamental to how reality works. Most profoundly, we discovered that space emerges from quantum entanglement. Regions that are strongly entangled are close in space. Regions that are not entangled are distant or disconnected. Geometry is not fundamental. It is derived from the pattern of information relationships. Space is a holographic projection from quantum information on a boundary. This leads to a new paradigm. The old view was that space and time are fundamental, and matter and energy exist within space-time, and information describes the state of matter and energy. The new view is that information is fundamental, and space and time emerge from information structure, and matter and energy are patterns in the information. What does this paradigm explain? It explains why quantum mechanics preserves information. Because information is what everything is made of, so it cannot be created or destroyed, only transformed. It explains why black holes must preserve information, because even extreme gravity cannot eliminate information, only reorganize it. It explains why there are holographic bounds on information storage, because information capacity is tied to surfaces, not volumes. It explains how space emerges from quantum mechanics, because entanglement creates geometric connections, It connects previously separate domains of physics. Thermodynamics, quantum mechanics, gravity, cosmology, all of these are unified in the information framework. They are all aspects of how information behaves, how it is stored, how it transforms, how it creates the structures we observe. What does this paradigm not explain yet? It does not fully explain the measurement problem, how definite outcomes emerge from quantum superpositions. It does not explain the initial conditions of the universe, why entropy started low. It does not explain dark matter or dark energy. It does not explain consciousness, though it might provide a framework for thinking about it. It does not give us a complete theory of quantum gravity, though it points the way. The paradigm is not finished. It is a work in progress. But it represents real progress, a genuine deepening of our understanding. We have answered an ancient question: what is the universe made of? And the answer is not matter or energy or even space-time. The answer is information. But we should be careful about what we mean by fundamental. When we say information is fundamental, we mean it is more basic than other things we thought were fundamental. Matter emerges from information. Energy emerges from information. Space emerges from information. But that does not necessarily mean information is the absolute bottom, the final answer. There might be something deeper than information. There might be principles or structures that we have not discovered yet that underlie information itself. The history of physics is a history of finding deeper and deeper layers. Molecules are made of atoms. Atoms are made of nuclei and electrons. Nuclei are made of quarks and gluons. Each layer seemed fundamental until we found the next layer beneath. Information might be the deepest layer we have found so far, but it might not be the absolute bottom. There might be no absolute bottom. Reality might be layers all the way down, each one emerging from something more fundamental. The turtle we're standing on stands on another turtle, and that turtle stands on another turtle, and it is turtles all the way down, as the old joke goes. But even if information is not the absolute final answer, it is clearly a more fundamental description than what we had before. It explains things that matter and energy and space-time could not explain. It connects things that seemed separate. It makes predictions that are being confirmed. It is real progress. And that is how science works. Science does not claim to have final absolute truth. Science claims to have better and better approximations to truth, deeper and deeper understanding, more and more powerful explanations. The information paradigm is our current best understanding. It might be replaced by something even deeper someday. But for now, it is the frontier of human knowledge about the fundamental nature of reality. So, what should we take away from all of this? What is the lesson of the last 3 hours? The lesson is that the universe is comprehensible. It is made of something, and we can figure out what that something is. It follows rules, and we can discover those rules. It has structure, and we can uncover that structure. The universe is not random chaos. It is organized information processing itself according to physical laws. The lesson is that information is more real, more concrete, more fundamental than we ever imagined. Information is not just something we use to describe reality. Information is reality at the deepest level we have reached. You are organized information. The planet you stand on is organized information. The light reaching your eyes is information in motion. All of it is patterns of qubits entangled in specific ways, creating the illusion of space and matter and time. The lesson is that physics and information science are merging into one discipline. The questions that physicists ask and the questions that computer scientists ask are converging. How does the universe process information? What are the limits of computation in our physical world? How does complex information structure give rise to phenomena like life and intelligence? These are now questions at the frontier of both fields. And the lesson is that we have come far, but we are not done. Every answer opens new questions. We have solved the black hole information paradox, but encountered the firewall paradox. We have shown space emerges from entanglement, but we do not fully understand measurement. We have discovered that information is fundamental, but we do not know what consciousness is or why the universe began with low entropy or what dark energy is. There is still mystery. There is still wonder. There is still discovery waiting. And that is not a flaw of science. That is the glory of science. We will never run out of questions because every answer reveals new depths, new puzzles, new frontiers. Chapter 20. Is information fundamental? We began 3 hours ago with a question. Is information fundamental to physics? Now, after travelling through quantum mechanics, black holes, holography, emergent space-time, entropy, quantum information, and the cutting edge of modern physics, we can finally answer that question with confidence. Yes, information is fundamental to physics. Information is more fundamental than matter. Information is more fundamental than energy. Information is more fundamental than space. Information is more fundamental than time. All of these things that we thought were primary, that we thought were the basic building blocks of reality, turn out to be secondary. They emerge from something deeper, and that something deeper is information. But let us be precise about what we mean by fundamental. We mean several things. First, information is conserved at the most basic level. The total amount of information in the universe never changes. It can be transformed, spread out, scrambled, made inaccessible, but never created or destroyed. This is what unitarity in quantum mechanics demands, and every test confirms it. Information conservation is as fundamental as energy conservation. Second, information is what determines what happens in quantum mechanics. When information about a particle's path exists, the particle behaves differently than when information does not exist. The presence or absence of information affects physical outcomes, not just our knowledge of those outcomes. Information is an active ingredient in the laws of physics, not a passive descriptor. Third, information is stored in space itself through holographic encoding. A black hole's information is on its horizon, not in its volume. The information in any region is bounded by the area of its boundary. Space does not contain information. Space is information organized in particular ways. Geometry emerges from information structure. Fourth, entanglement, the sharing of quantum information. is what creates spatial relationships. Objects are close in space because they are strongly entangled. They are distant because they are weakly entangled. Space itself emerges from the pattern of which qubits share information with which other qubits. Distance is a measure of information connectivity. Fifth, the laws of physics are rules for information transformation. Every interaction is information processing. Every field propagation is information transmission. Every measurement is information extraction. The universe is computing itself, updating its information state moment by moment according to the laws of quantum mechanics and relativity. Physical dynamics is information dynamics. So yes, information is fundamental. This is not speculation anymore. This is the conclusion that decades of theoretical work and experimental confirmation have led us to. Wheeler was right when he said "it from bit," though we now know it is more precisely IT from qubit. Physical reality emerges from quantum information. But we need to acknowledge the caveats. Information being fundamental does not mean we have a complete theory of everything. We still have open questions about quantum gravity, about measurement, about initial conditions, about dark energy and dark matter. The information paradigm is our current best framework, but it is not finished. Also, information being fundamental does not mean there is nothing deeper. There might be layers beneath information that we have not discovered yet. But those layers, if they exist, would have to explain why information appears fundamental at the level we can currently probe. Information is at least fundamental to the physics we understand. And information being fundamental does not automatically explain consciousness or free will or meaning or purpose. These might be related to information in some way, but we have not proven that. The connection between physical information and subjective experience remains mysterious. We should not oversell what the information paradigm tells us. With those caveats noted, let us celebrate what we have learned. We have discovered something profound about the nature of reality. We have seen that the universe is not made of tiny billiard balls bouncing around in empty space. It is not even made of quantum fields vibrating in a space-time continuum. At its deepest level, the universe is made of information, of bits or qubits, of answers to yes or no questions, of patterns of correlation and entanglement. And these patterns create everything. They create space by establishing distances. They create time by accumulating and dispersing. They create matter by organizing in stable structures. They create forces by allowing information exchange. They create complexity by integrating information across scales. They create life by learning to preserve and replicate information patterns. They create minds by integrating information in special ways. Everything you touch, everything you see, everything you are, is organized information. The screen displaying these words is information held in a particular pattern. The thoughts in your mind are information processing in your brain. The sensation of time passing is information becoming definite. The reality of space around you is entanglement structure. All of it is information, all the way down as far as we can see. This changes how you should think about yourself and your place in the universe. You are not a collection of atoms that happens to be arranged in a particular way. You are a pattern of information that has learned to preserve itself, to process inputs, to generate outputs, to maintain its structure against entropy. You are information that has become complex enough to know that it is information. The universe itself is information organizing, processing, transforming, creating structure from simplicity and complexity from structure. Every moment is a cosmic computation, the universe solving for what happens next, given what is happening now. And you are part of that computation. Your thoughts and choices and experiences are the threads in the vast tapestry of universal information processing. This is not a cold or reductionist view. It is not saying you are just a computer or that life is meaningless because it is all information. It is saying the opposite. It is saying that information can be unimaginably rich and complex. It can create beauty and consciousness and love and meaning. These things are not separate from information. They are what information does when it becomes sufficiently organized. We live in an information universe, and that makes the universe more wonderful, not less. Information is not cold abstraction. Information is the substance of reality, the thing that stars and planets and people are made of. Information is what makes the universe dynamic, changing, creative, evolving. Information is what makes it possible for the universe to compute itself, to generate structure, to create complexity, to give rise to life and mind. So, yes, information is fundamental to physics. That is the answer to the question we started with 3 hours ago. And the implications of that answer reach into every corner of existence, touching everything from the smallest quantum fluctuation to the largest cosmic structures, from the most basic physical processes to the most complex phenomena like life and consciousness. We have witnessed a profound shift in human understanding. We have seen physics transform from a science of matter and energy in space and time to a science of information and its organization. We have watched as concepts from computer science and information theory move from the periphery of physics to its very center. We have learned that the universe is not a machine. It is not even a quantum field. The universe is information processing itself, and this journey is not over. New discoveries await. New technologies will emerge from this understanding. New questions will open as old ones close. The frontier will advance, and future generations will see even deeper into the nature of information and reality. But for now, at this moment, we can say with confidence, we have learned something fundamental about what reality is. We have peeled back another layer and seen what lies beneath. And what lies beneath is not matter, not energy, not even space-time. What lies beneath is information. Pure, quantum, entangled, conserved, fundamental information. And that information is you and me and everything we see and everything we are. We are not in the universe. We are the universe knowing itself, the universe processing its own information, the universe asking questions about what it fundamentally is. And now you know the answer. You started this video wondering if information is fundamental to physics. Now you know that it is. More than that, you know why it is. You know how we discovered it. you know what it means. You have climbed the mountain with me step by step, from quantum weirdness to black holes to holography to emergent space-time, and now you stand at the summit, seeing the view that took physicists 50 years to reach. You will never see reality the same way again. Every object around you is organized information. Every moment is information processing. Every experience is information integrating in your mind. The universe is information, and information is the universe, and you are a pattern in that universal information structure, complex enough to understand that you are made of information. That is the answer. That is what we have learned. That is where physics has taken us. Information is fundamental. Reality is information. And you, dear viewer, are information that has become conscious of itself. Information wondering about information. The universe asking what it is made of and discovering that it is made of asking, of patterns, of knowledge, of information itself. Welcome to the information universe. You have always lived here. Now you know it.